Hello and welcome to Sleepy Science. Tonight, we are descending into the largest hidden world on Earth. A place of crushing pressure, living lights, underwater mountains, toxic lakes, lost cities, and creatures no human has ever seen alive. The deep ocean covers most of our planet, yet much of it remains unexplored, unmapped, and almost completely unknown. Across 100 calming and unsettling discoveries, we will uncover what survives in the darkness, what lies buried on the seafloor, and why this alien world may hold clues to the origin of life itself. Before we begin, tell me where you are listening from, and don't forget to like and subscribe. Now, leave the surface behind and follow me into the deep. The ocean has a layer where sound can travel for thousands of miles. Far beneath the waves, the ocean forms an invisible corridor where a single low sound can cross distances greater than entire countries. This region is called the SOFAR channel, and it exists because sound does not move through every part of the ocean at the same speed. Near the surface, warm water helps sound travel quickly, while colder water below slows it down. At greater depths, increasing pressure begins to speed it up again. Between these opposing effects lies a layer where sound moves at its slowest. When sound waves drift above or below this zone, they bend back toward it, becoming gently trapped rather than escaping toward the surface or the seafloor. A low-frequency call entering the channel can therefore travel for thousands of miles while losing surprisingly little energy. Scientists have used underwater microphones to detect distant earthquakes, volcanic eruptions, ships, and even the calls of whales moving across entire ocean basins. Some large whales may use these natural acoustic pathways to communicate over enormous distances, sending voices through darkness to animals they cannot see. Yet the same channel can also carry engine noise and industrial sound far beyond its source, spreading human activity into places that appear untouched. The SOFAR channel reveals that the sea is not an empty mass of water, but a carefully layered environment in which temperature and pressure create pathways no eye can follow. A sound may begin in one part of the world, curve silently through the deep, and arrive many hours later at a receiver beyond the horizon. What seems like silence from the surface may actually be a vast conversation still traveling beneath you. Most of the ocean has never been seen by human eyes. The largest unseen landscapes on Earth are not hidden on another planet. They are waiting beneath the water that surrounds our continents. Although maps often show the ocean floor covered with ridges, trenches, mountains, and plains, much of that picture comes from indirect measurements rather than close visual observation. Satellites can detect broad underwater features by measuring small changes in gravity and sea surface height, while sonar-equipped ships produce more detailed maps by sending sound toward the bottom and timing its return. But mapping a place is not the same as seeing it. Only a minute portion of the deep sea floor has ever been filmed directly by cameras on submersibles or remotely operated vehicles. Each expedition can examine only a narrow path, often illuminating a small circle of ground, while complete darkness remains on every side. Reaching these environments is difficult because seawater blocks normal radio communication, pressure can destroy poorly protected equipment, salt corrodes machinery, currents disturb navigation, and research ships are costly to operate. Even when a vehicle reaches the bottom, it may spend only a few hours exploring an area before beginning the long ascent. This means countless cliffs, caves, valleys, reefs, and wrecks may never have appeared in a human image. Some regions are known only as rough shapes on low-resolution maps, with their true textures and inhabitants still uncertain. The mystery should not tempt you to fill the darkness with invented creatures. The real uncertainty is more powerful. It means there are places on your own planet where evidence has barely begun to arrive. Human beings have crossed the ocean's surface for thousands of years, named its basins, and drawn boundaries across them, yet most of the world beneath those routes has never entered human vision. Earth may feel familiar only because we live on the thin part we can easily see. The deep ocean is the largest living space on Earth. Imagine a habitat so immense that every forest, Grassland, desert, and mountain ecosystem on land would seem like a narrow surface beside it. The deep ocean begins below roughly 200 meters and forms most of the ocean's volume, creating the largest continuous living environment on the planet. Unlike life on land, which is usually concentrated near the ground, marine life can occupy a three-dimensional world extending across vast horizontal distances and several kilometers downward. An organism may live suspended in open water without ever touching the seafloor or approaching the surface, while others inhabit slopes, sediments, underwater mountains, drifting particles, and the bodies of larger animals. This enormous volume is not equally crowded. Much of the deep sea contains relatively little food, so animals may be widely separated and forced to conserve energy for long periods. Yet emptiness does not make the habitat less important. It shapes how creatures hunt, reproduce, migrate, and survive. Some organisms travel vertically each day, while others remain within narrow depth ranges defined by temperature, oxygen, or available nutrients. Much of the deep ocean's biological work is performed by tiny organisms that cannot be seen without magnification. Microbes break down sinking material, recycle nutrients, and transform chemicals, quietly influencing the entire marine system. This reveals a truth that human perception often misses. The largest forms of life are not always the most important, and the busiest ecosystems are not always the greatest in scale. Because you live on land, continents feel like the natural center of the living world. But from the perspective of habitable volume, humanity occupies a thin boundary between rock and air. While most of Earth's potential living space lies inside water, we cannot enter without machines. When you look across the sea, you are seeing only the roof of an inhabited world, whose true size descends far beyond your sight. The deep ocean is not simply beneath life on Earth. In terms of available space, it is where most of life has room to exist. Creatures in the deep ocean have never seen sunlight. Long before sunrise reaches your window, countless animals are already living in a world where sunrise has never existed. Below the ocean's sunlit layers, light weakens rapidly as water absorbs and scatters it. And by the time you descend into the permanently dark depths, ordinary sunlight has disappeared completely. Many creatures born there spend their entire lives without seeing the sun, the moon, a cloud, or even the faint outline of the surface above them. Yet darkness does not mean that they experience an empty world. Their senses have simply developed around information other than daylight. Some detect tiny vibrations produced by swimming prey, while others follow chemical traces drifting through the water. Long feelers allow certain crustaceans to examine the space around them without needing to see it. And highly sensitive organs can reveal pressure changes caused by movement nearby. Eyes, when they remain useful, may become extremely large and sensitive enough to detect the weakest biological flash. In other species, vision has been reduced or lost because maintaining eyes requires energy that could be used for growth, reproduction, or surviving long periods between meals. Their colors can also seem strange from a human perspective. Red animals may appear almost black at depth because red wavelengths are absorbed near the surface, making a red body difficult for predators to distinguish in the darkness. Some creatures are dark enough to reflect almost none of the light that reaches them, turning their skin into natural camouflage against glowing hunters. Others rely on smell and touch so completely that the idea of visible appearance becomes nearly irrelevant to their lives. You may think of blindness as a disadvantage because your own world is built around sight, but that judgment comes from standing beneath a bright sky. In the deep sea, sunlight would be useless even if an animal could sense it, and survival belongs to those that can read subtler signs. These creatures remind you that nature does not build one perfect set of senses and distribute it to every form of life. It shapes awareness around whatever information an environment allows. To an animal that has never known daylight, darkness is not the absence of the world. Darkness is the world, complete with trails, warnings, movements, and signals that you would pass through without noticing. The ocean floor has mountains taller than Everest, The tallest mountain you have ever heard of may not be the tallest mountain on Earth when you measure from its true beginning. Mount Everest reaches the greatest height above sea level, rising nearly 9 kilometers into the atmosphere. But sea level is only a human reference line. Mauna Kea, the enormous volcanic mountain in Hawaii, begins deep on the Pacific seafloor and rises more than 10 kilometers from its submerged base to its summit. Most of the mountain is hidden beneath the ocean, so only its upper portion appears as an island. If the surrounding water vanished, Mauna Kea would stand higher from base to peak than Everest, revealing that some of Earth's largest mountains have remained concealed in plain sight. The ocean floor contains tens of thousands of seamounts, usually formed when magma rises through the crust and builds layer after layer of volcanic rock. Some remain entirely submerged, while others eventually grow tall enough to break through the surface and become islands. Over long periods, erosion, sinking crust, and changing sea levels can return an island to the water, leaving behind a flattened underwater mountain called a guyo. These flat summits are evidence that waves once struck land, now located far below the surface. Underwater mountains can also form long chains, as a tectonic plate slowly moves above a relatively fixed source of rising magma. The Hawaiian island chain records this process, with active volcanoes at one end and progressively older, more eroded mountains extending away across the seabed. These hidden peaks are not merely pieces of scenery. They redirect currents, force nutrient-rich water upward, provide hard surfaces where corals and sponges can attach, and create isolated habitats for species that may exist nowhere else. A single seamount can function like an island in the deep, concentrating life in an otherwise open region. Yet many never receive familiar names because they do not rise into the human world of maps, borders, and visible horizons. This changes the meaning of a mountain. You may instinctively imagine stone reaching toward the sky, but a mountain does not need air around it to be immense. Some of Earth's greatest elevations rise through cold water instead, carrying forests of coral rather than trees, and disappearing beneath a surface that makes their true scale almost impossible to feel. Everest dominates human imagination because you can see its summit against the sky, while larger base-to-peak structures remain concealed under waves. Perhaps grandeur has never depended on being visible. Perhaps visibility only determines which wonders humans remember. There are rivers and waterfalls flowing beneath the ocean. A river can flow through the ocean without mixing away, and a waterfall can plunge beneath the waves without ever touching the air. These underwater features do not usually consist of ordinary freshwater moving inside seawater. They form when differences in temperature, salt content, and suspended sediment make one body of water denser than the water surrounding it. On parts of the seafloor, extremely salty water leaks from buried salt deposits or forms when seawater becomes concentrated, creating brine so dense that it settles into channels and pools. Because the boundary between normal seawater and brine can be sharply defined, the heavier liquid may appear to have a surface of its own, complete with ripples, shorelines, and slow currents flowing like rivers along the bottom. Animals that enter some brine pools can be stunned or killed because the water contains very little oxygen and may carry toxic chemicals, while specialized microbes thrive around the edges. Other underwater rivers are produced by turbidity currents, fast-moving mixtures of water, mud, sand, and debris that rush down continental slopes. These flows can carve long submarine canyons, transport sediment far into the deep ocean, and sometimes damage communication cables lying across the seabed. Underwater waterfalls arise from the same basic principle of density. In the Denmark Strait between Greenland and Iceland, cold, dense water from northern seas spills beneath warmer Atlantic water and descends down a vast underwater slope. This hidden cascade falls several kilometers, making it far taller than any waterfall on land, although its movement is broad and submerged, rather than a narrow curtain of water. From the surface, nothing dramatic may be visible. There is no roaring cliff, no cloud of spray, and no riverbank to reveal where one body of water is moving beneath another. Yet below, Enormous masses of water are sliding, sinking, and continuing into the global circulation of the ocean. These processes transport heat, oxygen, salt, nutrients, and carbon between distant regions, influencing conditions far beyond the place where the descent begins. The spectacle is difficult to imagine because water seems like one continuous substance, but the ocean contains layers with distinct physical identities that can move past one another for long distances. What looks uniform from above is filled with boundaries, currents, and descending flows as structured as landscapes on land. The rivers have no visible banks, and the waterfalls make no sound that reaches the shore, but they are real enough to reshape the seafloor and help regulate the planet. They quietly challenge the simple idea that a river must run through land, or that a waterfall must fall through air, showing that nature often keeps the form of a familiar thing while changing almost everything you thought defined it. The deep ocean has its own weather system. Even where no wind can blow and no cloud can form, the deep ocean can shift from calm to violent, as if it were experiencing weather of its own. This is not weather in the atmospheric sense, but a changing system of currents, internal waves, eddies, and sediment-filled disturbances that can transform conditions along the sea floor. Far above, tides pull on the ocean, yet their energy does not remain near the coast. As tidal motion passes over underwater ridges and steep slopes, it can generate enormous internal waves that travel through hidden boundaries between layers of water. These waves may rise hundreds of meters while remaining almost invisible at the surface. When they break, they stir nutrients, redistribute heat, and disturb fine sediment that may have rested undisturbed for years. Scientists have also recorded powerful benthic storms, periods when currents near the bottom suddenly accelerate and sweep across broad regions of the abyss. The water may become filled with suspended particles, reducing visibility and changing the environment for animals that live on or within the sediment. Large rotating eddies can carry water with distinct temperatures, oxygen levels, and chemical properties into regions that were previously stable, creating slow-moving changes comparable to weather fronts. Underwater terrain shapes these events just as mountains influence winds on land. A ridge may redirect a current, a canyon may concentrate its force, and an isolated peak may create turbulence in the water passing around it. For deep-sea organisms, these changes can determine whether food arrives, whether sediment covers a feeding surface, or whether a normally quiet habitat becomes temporarily energetic. Some animals may benefit when currents deliver fresh material, while others retreat into burrows or cling more tightly to the bottom. Because these events happen far from human observation, scientists often discover them through long-term instruments that record temperature, current speed, and particle movement for months or years. The readings reveal a world that is not frozen in permanent stillness, but constantly rearranged by forces arriving from distant tides, planetary rotation, and the shape of the seafloor itself. The deep ocean has no rainstorm you could watch, and no thunder you could hear from the shore, yet it has calm periods, turbulent seasons, wandering fronts, and sudden disturbances. Its weather is written not across the sky, but through moving water, reminding you that an environment can be dynamic even when its surface appears perfectly peaceful. Some parts of the ocean are completely silent. There are moments in the deep ocean when a hydrophone records so little that the silence seems almost absolute, but complete silence beneath the sea is rarer than imagination suggests. Sound is constantly being created by distant waves, shifting ice, earthquakes, underwater landslides, ships, marine animals, and even the movement of water around the listening instrument itself. Yet some remote regions can become extraordinarily quiet, especially when they are far from shipping routes, severe weather, active coastlines, and noisy animal gatherings. In these places, the background sound may fall low enough for researchers to detect vibrations that would be hidden elsewhere. A faint whale call can arrive from far beyond visual range. A small earthquake may send a low pulse through the water. Shrimp, fish, and other animals can produce clicks, knocks, grunts, and scraping noises that reveal a hidden biological community. The quietest conditions often occur at particular depths and during periods when surface winds are weak, because rough seas transfer energy into the water as sound. But even then, the ocean has its own natural acoustic flaw. Water molecules move, distant geological events contribute low-frequency vibrations, and pressure changes pass through the sea. This means the phrase "completely silent" should be understood carefully. The ocean may become silent to human ears, because many of its sounds lie outside the range we naturally hear or are too weak for us to notice. But a sensitive instrument can still detect activity. Silence also depends on where and how you listen. A place that seems quiet during 1 hour may later fill with migrating animals, a passing storm, or the distant rhythm of propellers. In some deep habitats, sound is so important precisely because sight is limited. An animal may detect the approach of danger or the movement of prey through vibrations long before physical contact occurs. Human noise can therefore change a habitat that once had long periods of natural quiet, masking delicate signals and shrinking the distance over which animals can communicate. The most silent ocean regions are not truly empty of sound. They are places where the planet's quieter voices become audible. When machinery fades and surface turbulence weakens, you do not hear nothing. You begin to hear what was always there beneath the louder world. The pressure at the bottom would crush a human instantly. At the deepest point of the ocean, every small area of your body would be pressed by the weight of nearly 11 kilometers of water above it. The pressure near the bottom of the Mariana Trench is more than 1,000 times greater than the pressure you experience at sea level, strong enough to destroy ordinary equipment, collapse hollow structures, and force water through the smallest weakness in a vessel. Yet the common image of a human body being instantly flattened like an empty can is not completely accurate, because most of your tissues are made largely of water, and water does not compress easily. The greatest immediate danger would come from the air-filled spaces inside you. Your lungs, middle ears, sinuses, and any trapped pockets of gas would shrink dramatically as external pressure increased. Without controlled equalization and a protected environment, the damage would become fatal long before you reach the bottom. Lungs could collapse, delicate tissues could rupture, and gases dissolved in the body could create additional problems during changing pressure. This is why deep diving vehicles are not simply strong metal boxes. Their crew compartments are often built as thick pressure spheres, because a rounded shape distributes force more evenly than a flat wall. Materials must be tested for microscopic flaws, since a tiny weakness can grow into catastrophic failure under such extreme conditions. Outside the protected cabin, cameras, batteries, lights, and electronics require special housings or must be designed so that internal and external pressures remain balanced. Deep-sea animals avoid being crushed through a very different strategy. Many have few or no large gas-filled spaces, and their bodies contain flexible tissues that remain close to the pressure of the surrounding water. Their proteins and cell membranes are chemically adapted to function under conditions that would disrupt the biology of surface animals. This does not mean they are invulnerable. A species adapted to one depth may be damaged if brought upward too quickly, because its body has evolved for a narrow pressure range. Pressure in the deep ocean is therefore not merely a force pressing down from above. It is part of the environment's basic chemistry, influencing how bodies are built and how cells operate. An unprotected person could not survive there, but not because every part of the body would simply become flat in a single instant. The more accurate truth is quieter and more unsettling. Your body belongs to a thin layer of the planet where internal and external pressure remain gently balanced. Descend far enough, and the physical conditions that feel normal to you disappear, revealing how narrow the range of the human world truly is. There are lakes at the bottom of the ocean that kill most animals that enter. At first glance, it looks impossible. A dark lake resting inside the ocean, with a surface, an edge, and water that refuses to blend with the sea around it. These strange formations are called brine pools, and they appear when water loaded with unusually high concentrations of salt becomes much denser than ordinary seawater and settles into depressions on the seafloor. From a submersible, the boundary can resemble a shoreline, sometimes rippling when an animal touches it. But entering can be deadly. Many brine pools contain little or no oxygen, and some are enriched with methane or hydrogen sulfide released from sediments below. Fish and crustaceans that cross too deeply into this chemical trap may become stunned, suffocate, or die because their bodies cannot tolerate the sudden change in salinity and chemistry. Yet the scene is not simply one of death. Along the margins, bacteria convert methane and sulfur compounds into energy, supporting mussels, worms, and other organisms adapted to conditions that would destroy most familiar life. The pool is therefore both a barrier and a source of nourishment, lethal at its center, but crowded with specialists around its edge. It asks you to reconsider what makes a place habitable. Life does not always seek clean water, sunlight, or comfortable conditions. Sometimes it gathers beside poison, learns to use what others cannot survive, and turns the border of death into the foundation of an ecosystem. The deep ocean contains more history than any museum on Earth. Beneath the seabed lies an archive so vast that its oldest pages were written before humans, cities, or even modern coastlines existed. The record is stored in sediment, built slowly from material that falls through the ocean year after year. Volcanic ash, wind-blown dust, microscopic shells, pollen, soot, mineral grains, and the remains of organisms from the water above. Over immense spans of time, these particles form layers, with newer deposits generally resting over older ones. Scientists recover this hidden history by drilling or pushing coring tubes into the seafloor and bringing back long columns of mud. To an untrained eye, a core may appear dull and lifeless, but its chemistry can reveal ancient temperatures, changing ice sheets, shifts in rainfall, and periods when parts of the ocean lost oxygen. Fossil shells show which organisms once lived there, while ash layers can identify eruptions that darkened skies thousands of years ago. Dust may record the expansion of deserts, and tiny fragments of charcoal can preserve evidence of distant fires. The archive is imperfect because currents disturb sediment, and burrowing animals mix some layers. Yet comparisons between many cores allow researchers to rebuild patterns extending far beyond written memory. A museum preserves what people choose to save, but the ocean accepts whatever reaches it, from ordinary biological debris to traces of planetary catastrophe. Quietly and without intention, the seafloor has been documenting Earth's transformation one particle at a time, reminding you that history is not only written in books. Much of it is buried in darkness, waiting for someone to learn how to read mud. Shipwrecks on the ocean floor are preserved better than on land. A ship lost centuries ago can sometimes remain on the seafloor with wooden beams, cargo containers and tools still arranged around the moment its journey ended. This does not happen everywhere because the ocean can be brutally destructive. Waves break structures apart, salt water corrodes metal, currents scatter objects, and marine organisms bore into exposed timber. But in certain environments, the same sea becomes an exceptional preservative. Cold temperatures slow chemical and biological activity. Fine sediment buries delicate material, and low oxygen water prevents many decomposers and wood-eating animals from surviving. The deepest parts of the Black Sea provide a remarkable example. Their waters are largely without oxygen, and archaeologists have discovered ancient wooden vessels with masts, steering equipment, and construction details preserved far better than similar objects would have survived on land. Such wrecks are more than sunken ships. They can reveal trading networks, woodworking techniques, food storage, navigation, and the ordinary possessions of people whose lives left few written records. Yet preservation creates a difficult responsibility. An object stable underwater may begin to shrink, crack, or rapidly corrode when raised into air, so recovery can destroy what centuries of burial protected unless conservation begins immediately. For this reason, many sites are carefully photographed and studied where they lie. The ocean does not preserve a wreck out of kindness. It preserves it when decay is denied the oxygen, movement, and living organisms it needs. In those rare places, time does not stop, but it slows enough for a vanished human world to remain waiting below. The ocean floor is covered in a layer of ancient snow. A silent snowfall has been drifting through the ocean for longer than human beings have existed, but its flakes are not made of ice. Scientists call it marine snow, a continuous shower of dead plankton, fragments of algae, waste particles, mucus, dust, and tiny pieces of once living matter that sink from the upper ocean toward the depths. Some particles fall alone, while others stick together into soft clumps large enough to be seen moving through the water like pale flakes beneath a street lamp. Most are eaten, broken apart, or recycled before reaching the bottom, yet a small fraction completes the long descent and settles into the sediment. Layer by layer, this material becomes part of the seafloor, carrying carbon and nutrients away from the surface for years, centuries, or sometimes far longer. The journey can take weeks, and the falling particles rarely remain unchanged. Bacteria consume them, small animals tear pieces away, and transparent drifting creatures build temporary homes from sticky mucus before abandoning them to sink. For many deep-sea organisms, this slow rain is one of the main connections to productive waters far above. A sudden seasonal increase can bring a feast, while long periods of scarcity force animals to live on almost nothing. Marine snow also plays an important role in Earth's carbon cycle, because some of the carbon captured by organisms near the surface is transported downward and buried instead of quickly returning to the atmosphere. Yet the ocean floor is not covered by a clean white blanket. The phrase describes a process, not a literal landscape of snowdrifts. By the time the material arrives, it may be dark, fragmented, chemically altered, and mixed with mineral sediment. Still, every particle contains a history of movement through the living ocean. A microscopic shell may have once floated in warm surface water. A grain of dust may have crossed an entire continent before falling into the sea. A fragment of tissue may have passed through several bodies before reaching the bottom. What appears to be mud beneath the ocean is therefore not simply dirt. It is the accumulated remainder of countless lives and journeys, quietly settling into a record that grows thinner than paper each year. While the surface world celebrates visible seasons, the deep ocean experiences a slower one, measured by what descends from above. Its ancient snow never melts because it was never frozen. It simply falls, changes, feeds, and becomes part of the planet's memory. There are volcanoes erupting constantly on the ocean floor. Most volcanic activity on Earth happens where almost no human being can watch it. Along the enormous network of mid-ocean ridges, tectonic plates pull apart and allow molten rock to rise from beneath the crust, creating new seafloor through eruptions that often occur thousands of meters underwater. These ridges stretch for tens of thousands of kilometers, forming the longest mountain system on the planet. Yet much of their activity passes unnoticed, because the weight of the overlying water suppresses towering ash clouds and dramatic explosions. When lava meets cold seawater, its outer surface cools almost instantly, forming a dark crust, while molten material continues pushing from inside. This produces rounded structures known as pillow lavas, stacked across the bottom like enormous hardened cushions. Some eruptions spread lava across broad areas, while others build cones, ridges, or entire volcanic islands over time. The phrase constantly erupting does not mean that every submarine volcano is active at every moment. It means that somewhere along the vast and poorly observed oceanic system, volcanic activity is occurring with remarkable frequency, much of it never directly witnessed. Detecting these events can be difficult. Scientists may discover them through earthquake swarms, unusual sounds, chemical changes in seawater, floating debris, or later surveys showing fresh lava where older terrain once existed. Underwater eruptions can also release heat and minerals that alter nearby habitats, but they are first and foremost part of the machinery that renews Earth's crust. New rock forms at spreading ridges, gradually moves away, cools, and may eventually descend back into the planet at distant boundaries. In this way, the seafloor is continually created and recycled rather than remaining an ancient, unchanging foundation. Some submarine volcanoes are peaceful by volcanic standards, producing slow lava flows under immense pressure. Others can erupt violently, especially in shallower water where expanding steam and trapped gases have more room to accelerate. A few grow high enough to emerge above the waves, creating new islands that may later erode or sink beneath the surface again. This hidden volcanism changes how you imagine the solid Earth. The ground beneath the ocean is not a finished platform placed there in the distant past. It is an active surface, opening, cooling, breaking and rebuilding while life continues above it. From a ship, the sea may appear calm enough to reflect the sky, even as molten rock is entering water kilometers below. The planet does not need to display its violence for that violence to be real. Much of Earth's inner heat escapes in darkness, quietly manufacturing new ground beneath an ocean that conceals the process almost completely. The ocean has a zone where no light has ever reached. There is a depth where the sun disappears so completely that noon and midnight become physically indistinguishable. This region is called the aphotic zone, the part of the ocean where sunlight is too weak to support photosynthesis and deeper down is absent altogether. Its upper boundary is not fixed at one universal depth because water clarity changes from place to place. In clear tropical seas, faint sunlight may penetrate farther than it does in coastal water filled with sediment and plankton. But eventually, every downward ray is absorbed or scattered. Red wavelengths vanish first, followed by orange, yellow and green, while blue travels deepest before it too fades away. Below roughly 1,000 meters, sunlight is generally no longer detectable, and any natural light seen there is produced within the ocean rather than arriving from the sky. This distinction matters because the deep sea is not always visually black. Many organisms create bioluminescence through chemical reactions inside their bodies or through partnerships with glowing bacteria. Their flashes can attract prey, confuse attackers, identify mates, or illuminate objects for only a fraction of a second. A submersible may therefore encounter points, clouds, and moving patterns of light in a region the sun has never touched, turning darkness into a background for signals rather than an empty absence. Without sunlight, plants and algae cannot grow there, so most of the food available to animals must arrive from elsewhere or be produced through chemical processes in specialized environments. This limitation shapes the pace of life. Energy is often scarce, encounters may be rare, and wasting effort can be dangerous. Some hunters wait almost motionless for prey to approach, while other animals migrate upward at night to feed and retreat before morning. Inhabitants that remain permanently deep have never seen a sunrise reflected on water, never experienced a shadow cast by a cloud, and never used the changing position of the sun to measure a day. Their biological rhythms may instead respond to tides, food arrivals, internal clocks, or subtle changes carried down from distant surface cycles. You naturally associate light with activity, knowledge, and life because your own senses evolved in a bright environment. The aphotic ocean reveals that these associations are local rather than universal. A world can function without dawn, photosynthesis, or visible horizons, provided life finds other ways to gather energy and information. The darkness there is not a temporary night waiting for morning. It is an ancient condition that has shaped bodies, behaviors, and entire ecosystems, and perhaps that is what makes it so difficult to imagine. Not that nothing can live without sunlight, but that countless lives can unfold completely without ever knowing that the sun exists. Some deep-sea fish have eyes pointing upward to hunt silhouettes above. Above a deep-sea hunter, even the faintest remaining glow can turn another animal into a moving shadow. And some fish have evolved eyes built almost entirely to watch that narrow ceiling. Species such as barreleyes, tube shoulders, and certain hatchetfish possess tubular or strongly upward-facing eyes that collect light from above far more efficiently than ordinary round eyes. Instead of scanning every direction equally, they concentrate their vision where prey is most likely to betray itself. A shrimp, jellyfish, or small fish swimming overhead may block the dim background light and appear as a dark silhouette, allowing the hunter below to detect it before finer details become visible. Tubular eyes work somewhat like biological telescopes, gathering limited light through a narrow field and focusing it onto highly sensitive retinas. This design offers excellent upward vision, but it can make seeing sideways more difficult. So some species also have additional retinal structures that widen their awareness. The barreleye fish takes the adaptation even further. Its green, tube-shaped eyes sit inside a transparent shield on its head and can rotate, pointing upward while the fish searches and then turning forward when it moves to capture food. Looking upward also helps deep-sea animals recognize danger, since a descending predator may reveal itself against the weaker light above. Yet silhouettes create another evolutionary problem. Animals visible from below become easy targets, encouraging some species to develop narrow bodies, reflective sides, or carefully placed light organs that soften their outlines. The result is a silent contest between eyes designed to find shadows and bodies designed to erase them. To you, upward-facing eyes may appear strangely limited, but evolution does not build creatures for a complete view of reality. It builds them to notice the information that matters most. In a world where one faint outline can mean food, danger, or survival, seeing less of everything may be the price of seeing one direction extraordinarily well. Creatures here create their own light to survive in total darkness. In the deepest water, a flash lasting less than a second can become a weapon, a disguise, a warning, or an invitation. This living light is called bioluminescence, and it is produced when chemical substances react inside an organism, releasing energy as visible light with very little heat. In many animals, a molecule often called luciferin reacts with oxygen with the help of an enzyme, although the exact chemistry differs between groups. Some creatures manufacture the necessary compounds themselves, while others obtain them from food or depend on glowing bacteria housed inside special organs. The light is usually blue or blue-green, because those wavelengths travel most effectively through seawater, and because many deep-sea eyes are especially sensitive to them. A lanternfish can arrange small light organs along its body in patterns that may help members of its species recognize one another. A dragonfish can shine light ahead like a private search lamp, and certain species produce red illumination that many other deep-sea animals cannot detect, giving the hunter a secret form of vision. Some squid release clouds of glowing material instead of dark ink, confusing an attacker with a luminous decoy. Other animals flash when touched, perhaps startling a predator or attracting an even larger hunter that may attack the original threat. Bioluminescence can also hide a body rather than reveal it. By producing light on the underside that matches the faint brightness above, an animal can reduce its silhouette when viewed from below, a strategy known as counter-illumination. Creating light costs energy, so flashes are often brief, controlled, and used only when needed. Their timing, brightness, color, and position can carry information as precise as a gesture. What appears to you as scattered sparks may be an active language of pursuit, recognition, deception, and defense. These creatures do not illuminate the deep ocean as humans illuminate a city. They create only the exact light required for the next decision. In their world, darkness is not defeated by brightness. It is shaped by carefully measured signals, each one asking another life form to approach, retreat, hesitate, or disappear. Some animals in the deep ocean are completely transparent. A predator can look directly at a deep-sea animal and still fail to understand that anything is there. Transparency is common among jellyfish, comb jellies, larval fish, shrimp, and other creatures whose soft bodies allow light to pass through with very little scattering. The effect works because much of their tissue is made of water-rich material with optical properties close to those of the surrounding sea. Without thick skin, mineralized structures, heavy muscles, or dense pigments to reflect light, the animal produces only a faint outline and can almost vanish against open water. This is especially useful away from the seafloor, where there are no rocks, plants, or crevices behind which a small creature can hide. Yet becoming transparent is more difficult than simply removing color. Eyes must absorb light in order to function. Digestive organs contain visible food, and internal tissues often scatter light. Many transparent animals therefore remain partly visible through dark eyes, colored stomachs, or reflective organs. Some hide these unavoidable features inside narrow shapes, cover them with mirrored tissue, or position them so they are harder to see from common angles of attack. Others become transparent only during vulnerable stages of life and develop pigmentation as adults. Gelatinous animals are particularly suited to this strategy because their bodies require little rigid support in water, allowing them to remain soft, thin, and nearly invisible. Transparency also comes with limitations. A clear body may offer little protection from damage, and it cannot conceal an animal equally well against every background or from predators using senses other than vision. Some hunters detect movement, electrical signals, or chemical traces, making invisibility to the eye only one layer of defense. Still, in clear open water, removing your own appearance can be more effective than wearing any pattern. These animals challenge the human habit of imagining camouflage as color matching color. Sometimes the safest color is none at all, and survival depends not on resembling the surrounding world, but on allowing that world to pass through you almost unchanged. The giant squid has eyes the size of dinner plates. Imagine meeting an animal whose eye alone could nearly cover your face, then realizing that this enormous organ may have evolved not to find prey, but to notice death approaching. The largest documented giant squid eye measured about 27 centimeters across, roughly the width of a large dinner plate, with a pupil nearly 9 centimeters wide. No other known living animal has eyes of comparable size. At first, it seems obvious that larger eyes must simply provide sharper vision. Yet underwater vision does not improve endlessly as an eye grows. Beyond a certain point, an enormous eye offers little advantage when searching for small nearby prey. Its real strength is collecting extremely faint light across a wide region. Researchers have proposed that this allows giant squid to detect the movement of sperm whales, their most important predators, before the whales come close enough to strike. A diving whale disturbs tiny organisms in the surrounding water, creating a broad and faint visual signal that a smaller eye might miss. Models suggest that a fully grown giant squid may notice such a disturbance from more than 100 meters away, perhaps gaining enough time to turn, accelerate, or change direction. This would make the eye less like a magnifying glass and more like an early warning system built for detecting large moving threats. The squid's eyes are also positioned on opposite sides of its head, giving it an expansive view of the surrounding water, while a powerful lens focuses what little visual information is available. Building and maintaining such large organs requires energy and adds drag to the body, so evolution would not preserve them unless they offered a meaningful advantage. Scientists still study their exact function because observing giant squid behaving naturally remains exceptionally difficult, and much of what is known comes from recovered specimens rather than long-term encounters with living animals. Even so, their anatomy reveals that survival is sometimes determined not by how clearly you can examine what is close, but by how early you can sense something enormous moving far away. The giant squid's dinner plate eyes are not evidence that it sees a bright and detailed world. They may be evidence that, in its world, one distant shadow is important enough to reshape the entire body. Some deep-sea creatures can swallow prey larger than themselves. A black swallower can encounter an animal larger than its own body and respond not by retreating, but by attempting to fit the entire creature inside itself. This relatively small deep-sea fish possesses a wide mouth, flexible jaw connections, backward-pointing teeth, and an extraordinarily expandable stomach. Together, these adaptations allow it to seize prey that would appear physically impossible to consume and gradually draw the victim inward rather than swallowing it in one quick movement. Specimens have been found containing fish up to about twice the swallower's length and many times its weight, with the stomach stretched into a thin balloon-like sac around the meal. Its teeth help prevent struggling prey from escaping while the jaws work forward over the body, almost as though the predator is pulling itself around its food. Such extreme feeding makes sense in an environment where meals can be widely separated, and an animal may not know when another opportunity will appear. Instead of waiting for perfectly sized prey, the black swallower has evolved to treat a rare encounter as a chance worth taking. But this ability is not limitless, and the strategy can fail catastrophically. If the swallowed animal is too large to be digested quickly, it may begin decomposing inside the stomach. Gases produced during that process can inflate the predator, carry it toward the surface, and sometimes contribute to its death. Some known specimens were discovered only because an oversized meal turned their greatest adaptation into a fatal mistake. This makes the black swallower more than a biological curiosity. It demonstrates how evolution works without foresight. A flexible stomach is useful often enough to persist, even though the same behavior can occasionally destroy the animal using it. Nature does not design a creature to make perfect decisions. It shapes a body that succeeds more often than it fails. For the black swallower, survival depends on accepting a risk that seems almost unreasonable. When food finally appears, it may be safer to attempt the impossible than to remain hungry and wait for something smaller. Anglerfish males fuse permanently to females and share a bloodstream. For certain deep-sea anglerfish, finding a partner ends not with separation, but with two bodies becoming one living system. This extraordinary strategy occurs only in some groups of deep-sea anglerfish, not in every species carrying the name. The male is usually far smaller than the female and may spend much of his early life searching for the chemical signals that reveal her presence. When he finally reaches a suitable female, he bites into her skin and holds on. In species that form permanent attachments, the tissues around his mouth gradually merge with hers, their blood vessels connect, and the male begins receiving nutrients directly through the female's circulation. His digestive organs and other structures may shrink because he no longer needs to feed independently, but his reproductive tissue remains functional. He becomes a permanent source of sperm, ready when the female releases eggs, eliminating the risk that the pair might lose one another before reproduction occurs. Some females have even been found carrying several attached males at once. The most surprising part may be what does not happen. Her body does not reject his tissue as foreign in the way a vertebrate immune system would normally attack an incompatible transplant. Genetic research has shown that anglerfish species practicing permanent fusion have lost or altered important parts of adaptive immunity, including systems involved in recognizing and rejecting foreign cells. Species with less permanent forms of attachment show less extreme immune changes, suggesting that reproductive fusion and immune evolution develop together. This creates a biological trade-off that seems almost unimaginable from a human perspective. The fish gained the ability to unite unrelated bodies, but only by changing defenses that most vertebrates rely on for protection from disease. In the vast open water, where encounters between adults may be extremely rare, permanent attachment turns one successful meeting into lifelong reproductive access. What appears disturbing to you is neither romance nor cruelty in biological terms. It is a solution to distance. The male does not merely remain beside the female. He gives up much of his independent existence so that the possibility of reproduction will not disappear into the surrounding ocean. Two animals begin the encounter as strangers, but end it sharing blood, nourishment, and a future neither could secure alone. Some jellyfish in the deep ocean can live indefinitely. The most famous jellyfish said to live forever is neither truly invincible nor a creature of the deepest abyss, and the real science is stranger than the myth. The tiny species Turritopsis dohrnii, commonly called the immortal jellyfish, is found mainly in temperate and tropical marine waters, and has demonstrated an extraordinary ability in laboratories. When injured, starved, aged, or placed under severe stress, its free-swimming adult body can collapse into a small cyst-like form and rebuild itself as a juvenile polyp. From that earlier stage, the colony can produce new adult jellyfish, effectively reversing the usual direction of development. This is not ordinary healing. Specialized cells can change their roles, allowing adult tissues to be reorganized into the structures of a younger life stage. In principle, the cycle could be repeated many times, which is why scientists describe the species as potentially biologically immortal. But potentially is essential. The jellyfish can still be eaten, infected, damaged beyond recovery, or killed by environmental conditions before rejuvenation occurs. Researchers have repeatedly triggered life cycle reversal under controlled conditions. Yet this does not prove that any single animal survives forever in nature. Genetic studies suggest that DNA repair, cellular protection, stem cell renewal, and the control of aging-related processes may all contribute to its unusual transformation, although scientists are still working to understand how these mechanisms cooperate. The discovery matters because most animals travel through development in one direction: embryo, juvenile, adult, decline. Teratopsis shows that an adult body plan does not always have to be the final destination. It can dismantle its present form and return to an earlier biological state, without recreating itself from a new fertilized egg. You should therefore imagine its immortality not as one ancient jellyfish drifting endlessly through the sea, remembering centuries of experience, but as a living process capable of repeatedly resetting its structure. The individual form disappears so that the biological cycle can begin again. Perhaps that is the most unsettling part of the discovery. Defeating aging may not require preserving the body you have, but surrendering it completely and becoming something younger that no longer carries the same shape. The Dumbo octopus flaps, ear-like fins to move through the dark. A Dumbo octopus does not race through the water like a torpedo. It moves with the measured rhythm of an animal for which every unnecessary effort has a cost. The name refers to several species of finned octopuses, including members of the genus Grimpoteuthis, whose rounded fins project from the mantle above the eyes and resemble a pair of ears. These fins are supported by internal cartilage and powered by strong muscles, allowing the animal to propel itself by rotating or gently flapping them. Its arms are joined by a broad web of skin that can open like an umbrella, helping it steer, brake, hover, and control its position above the bottom. Rather than depending mainly on the forceful jet propulsion used by many shallow water octopuses, Dumbo octopuses can combine fin swimming, movements of the arm web, drifting, and slow crawling. Observations of living serrate octopuses show that they may rest on the seafloor, rise when disturbed, spread or contract their web, and rapidly rotate their fins during stronger escape movements. This flexible system suits a soft, neutrally buoyant body, living where meals can be irregular and replacing spent energy may take time. Slow fin strokes allow the animal to travel without repeatedly forcing large amounts of water through its mantle, while the web provides fine control when approaching small prey or settling onto uneven ground. The fins are therefore not decorative additions and do not function exactly like the wings of a flying animal. They are underwater control surfaces, shaped to push against dense water and maintain stability with limited effort. Different species vary in size, body form, depth, and behavior, so the popular image of one universal Dumbo octopus hides a diverse group of animals. Some have been recorded several kilometers below the surface, and serrate octopuses include the deepest living octopods yet observed. Their gentle appearance can make them seem fragile, but their movement reveals precise engineering. Flexible where rigidity would waste energy, controlled where speed would offer little advantage, and powerful only when circumstances demand it. Watching one pass through the water may feel peaceful, yet that calmness is not laziness. It is an economical answer to an environment where survival may depend less on moving quickly than on never spending energy without a reason. Some fish in the deep ocean have no eyes at all. A. Fish can lose the face you expect it to have and still remain fully connected to everything moving around it. The statement that some deep-sea fish have no eyes is broadly true only with an important qualification. In many species, the eyes are not entirely absent but have become extremely small, buried beneath skin, reduced to light-sensitive remnants, or transformed into organs that no longer create ordinary images. The faceless cusk eel, Typhlonus nasus, appears to have no visible eyes when viewed from outside, contributing to its unfinished, almost featureless appearance. In grid-eye fishes of the genus Hypnops, the usual rounded eyes have been replaced by flattened sensory plates on top of the head. These modified organs are thought to detect changes in illumination, rather than form detailed pictures. When vision offers too little useful information to justify the energy required to build and maintain complex eyes, natural selection can favor bodies that invest more heavily in other senses. Fish possess a lateral line system made of sensitive structures that detect tiny movements and pressure changes in the surrounding water. Through it, an animal can register a nearby swimmer, follow a current, orient its body, or sense disturbances without seeing their source. Chemical sensors can reveal food, predators, or potential mates through dissolved molecules, while sensitive touch receptors and elongated fin rays may help some bottom-dwelling species inspect the sediment around them. Losing useful vision does not leave such an animal trapped in an empty world. It changes the kind of world available to its nervous system. A moving body becomes a pressure pattern, a meal becomes a chemical trail, and nearby terrain becomes a sequence of currents and contacts. Eye reduction also reveals that evolution does not always move toward greater complexity. An elaborate organ can become a disadvantage when its construction consumes resources but contributes little to survival. Over many generations, mutations that reduce such a cost may persist, provided other senses can perform the necessary work. Yet complete eye loss is not universal in the deep sea. Many species retain highly sensitive or unusually specialized visual systems because even a rare source of light can carry valuable information. The deep ocean therefore produces opposite solutions. Some animals enlarge and refine their eyes, while others reduce them almost beyond recognition. Neither path is more advanced. Each is an answer to a particular way of living. What looks like blindness to you may be a different form of awareness, built to notice a world your own eyes could never interpret. Certain deep-sea worms can survive in conditions that would kill most life. On the walls of an active hydrothermal chimney, the Pompeii worm lives where the surrounding water can change from cold to dangerously hot within the length of its body. Known scientifically as Alvanella pompejana, this pale, bristled worm builds a tube directly against mineral structures formed by vent fluids along the East Pacific Rise. Its home exposes it to rapid temperature shifts, low oxygen, acidic conditions, sulfides, and dissolved metals that would damage the cells of most animals. Early reports sometimes suggested that the worm could endure temperatures near boiling, but later experiments produced a more careful picture. It is exceptionally heat tolerant, yet prolonged exposure above roughly 50 degrees Celsius can still become lethal. The worm survives not by resting inside the hottest vent fluid, but by occupying narrow zones where cold seawater mixes with warmer chemical flows, moving within its tube as conditions change. Its cells produce protective molecules that help proteins keep their shape during heat stress, while unusual biochemical defenses may reduce damage caused by toxic compounds and microbes. A thick coat of bacteria also grows across hair-like structures on its back. Scientists are still investigating the full relationship, but these microbial partners may help process chemicals, provide protection, or contribute nutrients within this unstable habitat. The worm's tube offers another layer of control, creating a small boundary between its body and the most violent fluctuations outside. None of these adaptations makes it indestructible. Instead, They allow it to survive inside a narrow moving refuge where a few centimeters can separate tolerable water from fatal exposure. The Pompeii worm therefore teaches you that life at an extreme is rarely a heroic resistance to one unchanging danger. It is often the ability to sense invisible boundaries, cooperate with other organisms, protect delicate chemistry, and remain close to destruction without crossing fully into it. The vampire squid is neither a squid nor an octopus. Its name sounds like a creature invented to frighten sailors, yet the vampire squid is a quiet survivor from a branch of cephalopod evolution that almost completely disappeared. Vampiroteuthis infernalis belongs to its own order, Vampiromorpha, and is the only living representative of an ancient group related to both squids and octopuses without being a true member of either. Like an octopus, it has 8 arms joined by a broad web, but it also carries a pair of long retractile filaments, unlike the hunting tentacles of ordinary squid. These filaments can extend far beyond the body and collect tiny particles of organic material drifting through the water, which are drawn inward and combined with mucus before being eaten. This is remarkably different from the active predatory behavior suggested by its name. Its soft body is usually only about the size of a football, and it lives in oxygen-poor midwater regions where many fast predators struggle to remain active. The vampire squid survives there through an unusually slow metabolism and a highly efficient respiratory system. Its blood contains a copper-based oxygen-carrying pigment that works effectively even when oxygen levels are extremely low, while large gills help extract what little is available. When threatened, it can draw its webbed arms over its body, exposing rows of harmless finger-like projections called cirri, and making itself appear larger and more difficult to attack. It does not drink blood, stalk large victims, or behave like the monster implied by its Latin name, which translates roughly as the vampire squid from hell. Its unsettling appearance hides an animal built around patience, efficiency, and avoidance rather than violence. The vampire squid reminds you how easily a name can become more memorable than the organism itself. Once the frightening label is removed, what remains is not a demon of the deep, but the last living page of an evolutionary story whose other chapters have vanished. Some deep-sea creatures have no stomach. They absorb nutrients through their skin. A bone-eating worm can enter the skeleton of a dead whale without possessing teeth, a mouth, or even a stomach. These worms belong to the genus Osedax, and adult females survive through a feeding system unlike the digestive tract of almost any familiar animal. Their bodies extend colorful plumes into the seawater, while branching root-like tissues grow deeply into the bone beneath them. Those roots release acids that help dissolve the hard minerals surrounding the bone's stored fats and proteins. Nutrients then pass through the root tissues, making the common description that the worms feed through their skin partly true, though the process occurs through a highly specialized organ rather than across the entire outer body. Bacteria living inside the roots assist with the complex task of using compounds obtained from the bone. Some studies suggest that these partners help process fats and other nutrients the worm could not exploit as efficiently alone, while the host supplies them with a protected place to live. The arrangement is so complete that Osedax has abandoned the ordinary sequence of biting, swallowing, and digesting food inside a gut. Its food remains outside the body while the body grows into it. Even reproduction follows an unusual pattern. In many species, microscopic males live within the female's tube, sometimes in large numbers, while the much larger female continues excavating the bone. Over time, colonies of these worms can break down whale skeletons that might otherwise remain on the seafloor for decades, changing how long the remains are available to other organisms and how nutrients return to the surrounding ecosystem. Calling them bone eaters is therefore accurate, but they do not eat in the way the word usually suggests. They dissolve, absorb, and cooperate, turning another animal skeleton into both habitat and nourishment. Through Osedax, you encounter a form of life that has removed what seems like an essential organ and replaced it with roots and microbial partners. It quietly asks whether an individual organism must perform every task itself, or whether a body can become complete only through the lives it carries within it. There are fish that produce their own antifreeze. Fish swimming through polar seawater may carry ice crystals inside its body and still remain alive because its blood contains a natural defense against freezing. Antarctic notothenoid fish produce antifreeze glycoproteins, specialized molecules that attach themselves to the surfaces of tiny ice crystals before those crystals can grow large enough to damage cells and tissues. They do not warm the fish, and they do not work exactly like the antifreeze poured into a vehicle. Instead, they interfere with the orderly addition of water molecules to an ice crystal, allowing body fluids to remain liquid even when the surrounding seawater is cold enough to freeze ordinary fish blood. This protection became especially important as Antarctic waters cooled over millions of years and sea ice became a permanent danger. Remarkably, research suggests that the antifreeze gene in these fish evolved from part of a gene that originally helped produce a digestive enzyme, showing how evolution can repurpose existing biological material for an entirely new task. The proteins are produced in several tissues and circulate through the blood, but the system has a hidden complication. Ice crystals that enter the body may remain present because antifreeze proteins can also prevent them from melting easily when temperatures rise slightly. The fish therefore live with microscopic ice held in a controlled state rather than simply eliminating it. Antifreeze is only one part of their survival, since their enzymes, membranes, metabolism, and behavior must also function in extreme cold. These animals reveal that evolution does not always defeat a threat by removing it. Sometimes it changes the rules around the threat, allowing ice to enter the body while preventing it from becoming destructive. What would be a fatal accident for most fish has become a manageable part of everyday life in the polar sea. Some deep ocean animals have lived, unchanged for hundreds of millions of years. When a living coelacanth was brought to the attention of scientists in 1938, it appeared as though an animal had returned from a world believed to have vanished with the dinosaurs. Coelacanths were known from fossils extending back hundreds of millions of years, and their entire lineage had been assumed extinct because no younger fossils had been recognized after the end of the Cretaceous period. The modern genus Latimeria retains a body plan that resembles many ancient relatives, including thick, fleshy fins supported by internal bones, a distinctive three-lobed tail, and an unusual joint within the skull. This resemblance led to the popular description of the coelacanth as a living fossil, but saying that it has remained completely unchanged would be misleading. Modern coelacanths are not identical to their earliest ancestors, and the fossil record contains extinct members of the group with different shapes, sizes, and ecological roles. Evolution never stopped acting on them. Their genomes continued accumulating changes, populations separated, and living species adapted to particular deep rocky habitats. What remained comparatively conservative was the general architecture of the body, perhaps because it continued to function effectively within a relatively stable way of life. Genetic research has found that many coelacanth protein-coding genes evolved more slowly than those of several other vertebrate groups, although not every part of the genome changed at the same rate. This makes the coelacanth valuable, not because it is a frozen ancestor of land animals, but because it preserves a rare combination of ancient characteristics and modern adaptations. It reminds you that evolution does not demand constant visible redesign. A lineage can change continuously at the genetic and physiological level, while its outward form remains recognizable across immense spans of time. What survives is not an animal untouched by history, but a design that history never completely forced to disappear. The barreleye fish has a transparent head with rotating eyes inside. For decades, scientists examined barreleye fish preserved in jars, without realizing that the specimens were missing the structure that made the animal truly extraordinary. The soft, transparent dome covering the head of Macropina microstoma is easily damaged when the fish is caught in nets or brought to the surface, so early specimens appeared to have exposed tubular eyes fixed permanently toward the top of the skull. Only observations of living fish by remotely operated vehicles revealed the complete anatomy. The bright green eyes are enclosed inside a clear, fluid-filled shield and can rotate from an upward position to face forward when the fish feeds. The dark marks that look like eyes near the mouth are actually olfactory openings comparable to nostrils. Its real eyes sit farther back inside the dome, protected from direct contact with the surrounding water. Researchers have suggested that this shield may help defend the delicate visual organs when the fish searches near the stinging tentacles of siphonophores, colonial animals that capture small prey. The barreleye may hover almost motionless beneath them, using broad fins to maintain precise control while collecting food trapped among the tentacles or intercepting drifting organisms nearby. When it changes position to eat, its eyes rotate so that vision remains aligned with its small mouth. The transparent head is therefore not an empty bubble or an exposed brain, as misleading images sometimes imply. It is a specialized optical chamber that gives the eyes room to move while protecting them within a stable environment. The discovery also offers a warning about how scientific knowledge is formed. An animal removed from its habitat may lose the very feature needed to understand it, leaving researchers with an incomplete body and a confident but mistaken interpretation. Sometimes the mystery is not hidden because nature made it impossible to see, but because the act of collecting the evidence accidentally erased the answer. Hydrothermal vents create ecosystems that need no sunlight at all. When scientists first encountered crowded animal communities around hydrothermal vents in the late 1970s, they were looking at an ecosystem that should not have existed according to the familiar rules of life. Far below the reach of sunlight, enormous tube worms, clams, mussels, shrimp, crabs, snails, and microbial mats surrounded openings in the seafloor where heated, mineral-rich water emerged from the crust. Until then, nearly every major ecosystem known to science appeared to begin with photosynthesis. Plants or algae captured sunlight, produced organic matter, and supplied energy to animals farther along the food web. The vent communities revealed another starting point. Here, microorganisms form the biological foundation by using energy available in chemicals released from the earth. Some grow freely on rocks and chimney surfaces, while others live inside or upon larger animals, supplying nutrients in exchange for shelter and access to useful compounds. Grazers consume microbial films, filter feeders collect suspended cells, predators hunt the animals gathered around the vent, and scavengers recycle what dies. In this way, a complex community can rise around geological activity without plants, leaves, or daylight. Yet these habitats are not peaceful gardens preserved forever. Individual vents can weaken, shift, become blocked by minerals, or stop flowing as volcanic systems change beneath them. When the chemical supply fades, animals may die or disperse, leaving behind an empty chimney that once supported thousands of lives. New vents can appear elsewhere, and their first colonists may arrive as drifting larvae carried by currents from sites separated by great distances. Different species often dominate during different stages, so the ecosystem develops through a changing sequence rather than appearing fully formed. Even neighboring chimneys can support distinct communities because their temperatures, flow rates, and chemical mixtures differ. The phrase "needs no sunlight" also requires one careful distinction. Local food production occurs without light, but many vent microbes use oxygen that entered the deep sea from waters connected to the surface. The community is therefore independent of direct sunshine without always being completely isolated from the planet above. Its deepest lesson is not that sunlight is unimportant, but that life can organize itself around more than one source of usable energy. A vent transforms cracks in rock into the foundation of a food web, showing you that an ecosystem does not begin with a particular object such as a tree or a blade of grass. It begins wherever energy, matter, and living chemistry can meet long enough for relationships to form. The chemicals, pouring from deep-sea vents, are hot enough to melt lead. Stream of water hot enough to melt solid lead can erupt into an ocean only a few degrees above freezing without becoming a cloud of steam. At some black smoker hydrothermal vents, fluids emerge at temperatures approaching or even exceeding 400 degrees Celsius, while lead melts at roughly 327 degrees. The title is therefore physically plausible, although it is the superheated fluid carrying dissolved chemicals, not the chemicals as separate objects, that reaches this extraordinary temperature. The process begins when seawater penetrates fractures in young oceanic crust. As it descends, it approaches hot rock and magma, becomes heated under immense pressure, and reacts with the minerals surrounding it. Oxygen and magnesium are removed from the water, while sulfur, iron, copper, zinc, and other substances can be drawn from the rock into the fluid. Because the pressure is so great, the water can remain liquid at temperatures that would make it boil violently at the surface. It then rises through cracks and escapes into the near-freezing ocean. The dramatic black cloud is not smoke and is not usually composed of molten rock. As the hot fluid meets cold seawater, dissolved metals and sulfur rapidly combine and solidify into microscopic mineral particles. These particles darken the plume and gradually accumulate around the opening, constructing chimney walls from the same material that once traveled invisibly inside the fluid. Some chimneys grow into towers tens of meters tall, but they can also fracture, collapse, become sealed, or be rebuilt as the flow changes. The temperature difference across a very small distance can be extreme. Fluid inside an opening may be hundreds of degrees, while the water only a short distance away is cold enough to numb an unprotected human body. This does not mean that animals live directly within the hottest jets. Most occupy cooler mixing zones where vent fluid has already blended with seawater. The chemistry can also be acidic, corrosive, and rich in substances toxic to many forms of surface life. Instruments sent into these flows require carefully selected materials, and even temperature probes can be damaged if inserted improperly. What makes the vent especially fascinating is that its black plume is evidence of an event happening almost instantly. Minerals that were dissolved inside Earth encounter a radically different environment and become solid before your eyes. A hydrothermal chimney is therefore not merely a hot spring beneath the sea. It is a place where seawater enters the crust, is chemically rewritten by rock and heat, and returns carrying pieces of the planet's interior. The cold ocean surrounds this process without extinguishing it, as though fire and water have found a way to occupy the same point in space without either one fully winning. Life around hydrothermal vents survives on chemistry instead of sunlight. A world without green plants can still manufacture food, provided certain microbes know how to harvest energy from matter itself. Around hydrothermal vents, bacteria and archaea perform chemosynthesis, using reactions involving substances such as hydrogen sulfide, hydrogen, methane, or dissolved iron to obtain energy. They then use that energy to build organic molecules from carbon dioxide, performing the essential ecological task that plants carry out with light at the surface. The chemicals are not food in the ordinary sense. They are sources of electrons that can be transferred through controlled reactions inside microbial cells. The released energy is captured rather than lost, allowing the organisms to assemble carbon into material from which living tissue can grow. Different microbes specialize in different chemical pathways, because vent fluids vary from one site to another. Some form thick mats on rocks, some drift within the water, and others enter intimate partnerships with animals. Giant tube worms offer one of the clearest examples. As adults, they possess neither a mouth nor a conventional digestive system. Instead, a large internal organ called the trophosome is packed with chemosynthetic bacteria. The worm's red plume absorbs oxygen and hydrogen sulfide from the surrounding water, and specialized blood molecules transport both compounds to the bacteria without allowing the sulfide to poison the host. The microbes use them to produce organic nourishment, while the worm provides a stable home and a continuous chemical supply. Vent mussels and clams can also house helpful microbes in their gills, while certain shrimp cultivate bacteria on their bodies and harvest the growth. Other animals do not perform chemosynthesis or host microbial partners at all. They eat the microbes, consume animals that depend on them, or prey upon those consumers. Chemistry thus enters the community through tiny cells and moves outward into increasingly complex bodies. This system should not be confused with animals feeding directly on heat. Heat can speed or disrupt reactions, but it is the difference between chemical substances that provides usable energy. Vent life gathers where reduced compounds from beneath the crust encounter oxidized seawater, creating an imbalance that microorganisms can exploit. When the substances reach equilibrium, the opportunity diminishes, so life depends upon the continued meeting of fluids that have followed different histories. This is one reason vents interest researchers studying the possible beginnings of life. Mineral surfaces, natural chemical gradients, and continuous geological energy could have supported important prebiotic reactions on the early Earth. That possibility remains under investigation and does not prove that life began at a vent, but it expands the range of environments in which scientists can seriously search. Chemosynthesis changes the meaning of nourishment. It shows that life does not consume energy as a thing already prepared for it. Living systems recognize differences in the environment and build machinery capable of using them. Sunlight is one such difference, but it is not the only one. Beneath the ocean, life survives because microbes learn to turn the unfinished chemistry of a restless planet into flesh. Cold seeps on the ocean floor leak methane and support unique life. The seafloor can slowly bleed fuel from beneath its surface for centuries, creating crowded islands of life where the surrounding mud may appear almost empty. These places are called cold seeps, although cold only means that their escaping fluids are not heated to the extreme temperatures found at hydrothermal vents. Methane, hydrogen sulfide, oil-like hydrocarbons, and salty water can rise through cracks after being produced or trapped within deeply buried sediments. The flow may be so gentle that it resembles a slow exhalation rather than an eruption. Yet over time, it transforms the seabed. Microorganisms living below the surface consume much of the rising methane before it escapes into the water, often working together in communities that also use sulfate from seawater. Their activity can produce bicarbonate, encouraging calcium carbonate to harden within the sediment. What begins as soft mud may gradually become slabs, crusts, and rocky structures that provide attachment points for animals. Mussels, clams, tube worms, snails, crabs, and many smaller species can gather around these newly formed habitats, some relying on microbial partners housed inside their tissues. Because seepage may continue for decades or centuries, cold seep communities can persist far longer than many short-lived vent systems, developing complex patterns of colonization as the chemistry changes. The strongest flow may first support dense microbial mats and specialized shellfish, while older areas can become carbonate reefs occupied by corals and sponges after the seep weakens. Not every molecule of methane reaches the ocean or atmosphere. The sediment community acts as a biological filter, consuming a substantial portion underground. This makes cold seeps important not only as habitats, but also as part of Earth's carbon cycle. They reveal a landscape shaped by movement too slow for human senses to notice. You might watch the same patch of seabed for an hour and see almost nothing change. Yet beneath it, gas is migrating, minerals are forming, and organisms are quietly intercepting material that has traveled upward through layers of geological time. A cold seep is therefore not simply a leak. It is a place where the deep earth enters the living world gradually enough for an entire community to grow around the wound. There are frozen methane structures on the ocean floor that can burn. A pale chunk lifted from beneath the seafloor can look like ordinary ice, yet when a flame is brought near it, fire may dance above the melting surface. This material is methane hydrate, sometimes called fire ice, and it forms when methane molecules become trapped inside cage-like structures built from water molecules. The methane is not chemically bonded to the water in the usual sense. It is physically enclosed within the frozen framework. These structures remain stable only where temperatures are low and pressures are high, conditions commonly found beneath deep ocean sediments and in frozen ground on land. Much of the seafloor hydrate is buried rather than lying exposed as glittering blocks, and its distribution depends on local geology, methane supply, water depth, and temperature. If a recovered sample is brought into lower pressure or warmer surroundings, the crystal framework begins to break apart, releasing methane gas and liquid water. The methane can then burn, creating the strange appearance of ice-producing flame. It is the escaping gas that catches fire, not frozen water itself. Gas hydrates store a vast quantity of methane in a compact form, which has led researchers and governments to investigate them as a possible energy resource. Extracting that gas safely, however, is technically difficult. Destabilizing hydrate-bearing sediment can change pore pressure and weaken the surrounding ground, while uncontrolled gas movement could create hazards for wells and subsea infrastructure. Methane is also a powerful greenhouse gas, but the popular image of warming oceans suddenly releasing all seabed methane into the atmosphere is misleading. Many deposits lie deep beneath sediment. Only some regions are vulnerable to present-day warming, and methane escaping underwater may dissolve or be consumed by microbes before reaching the air. The scientific concern is real, but it depends on depth, location, rate of change, and the pathways available to the gas. Fire ice therefore sits between several identities: mineral-like solid, potential fuel, geological hazard, and frozen reservoir of ancient carbon. Its appearance encourages you to think of solids as permanent, yet methane hydrate survives only while the surrounding world maintains a precise balance. Change the pressure or temperature, and what seemed like stone becomes water and invisible gas. The flame is dramatic, but the deeper revelation is quieter. Even the seafloor can store instability in the shape of ice. The ocean floor contains more metals than all landmines combined. Scattered across parts of the abyss are billions of dark stones that grew around shark teeth, shell fragments, and grains of sand so slowly that a human lifetime would barely add a visible layer. These are polymetallic nodules, rounded deposits rich in manganese and iron that can also contain nickel, copper, cobalt, lithium, and rare earth elements. The claim that the ocean floor contains more metals than every landmine combined is too broad to be literally true for all metals, but it reflects an astonishing reality. Estimates suggest that nodules in the Clarion-Clipperton zone alone contain greater tonnages of several critical metals than are currently listed in global terrestrial reserves. This does not mean all of that material can be recovered, used, or treated as proven ore. A geological resource is an estimated natural concentration, while a reserve is the portion considered economically and technically recoverable under specific conditions. The ocean also stores metals in cobalt-rich crusts, coating underwater mountains, and in massive sulfide deposits formed where mineral-bearing fluids once emerged from the crust. Together, these deposits have attracted attention because modern batteries, electrical systems, alloys, and renewable technologies require growing supplies of nickel, cobalt, copper, manganese, and related materials. Nodules may appear easy to collect because they rest loose on soft sediment rather than being buried deep inside rock, but the apparent simplicity hides a profound environmental problem. They grow over millions of years and provide hard surfaces in places where exposed rock is rare. Sponges, corals, anemones, microbes, and other animals may live on, beneath, or around them, while many species in nodule fields remain undescribed. Industrial collectors would remove the nodules together with the upper sediment, produce spreading plumes, create noise, and alter habitats that recover extraordinarily slowly. Even after small experimental disturbances, tracks can remain visible for decades. The debate is therefore not merely about whether the metals exist. It is about whether humanity can accurately value a resource before understanding the ecosystem that contains it. Land mining carries severe environmental and social costs, but that does not automatically make deep-sea extraction harmless. Comparing the two requires evidence about energy use, waste, biodiversity loss, metal recovery, and long-term damage rather than promises from either side. The stones below may hold enough material to reshape future industries, yet their greatest value may not be measurable only in tons. They are also products of immense time, pieces of habitat, and records of chemical processes that cannot be replaced on any human schedule. The ocean floor may indeed contain more of certain metals than the mines we have already counted on land, but abundance does not answer the harder question of whether everything that can be taken should become ours. Manganese nodules have been growing on the ocean floor for millions of years. A dark stone no larger than a potato may have begun growing before the first human ancestor ever walked upright. Manganese nodules form on broad areas of the deep sea floor when thin layers of manganese and iron compounds slowly gather around a tiny central object, which may be a shark tooth, a fragment of shell, a piece of bone, or an ordinary grain of rock. Some metals arrive directly from seawater, while others are released from sediment beneath the nodule and carried upward through water trapped between the grains. Layer after layer accumulates around the nucleus, giving a cut nodule a structure resembling the rings of an ancient tree. But the pace is almost beyond human intuition. Many grow only a few millimeters in a million years, and some potato-sized examples are tens of millions of years old. Scientists estimate that many nodules found today began forming between 8 and 32 million years ago. Their slow growth raises a puzzling question. If sediment is constantly falling onto the seabed, why are they not buried? Part of the answer may be that nodules are most common where sediment accumulates extremely slowly. Burrowing animals can also disturb and redistribute the upper layer, while currents and chemical processes may help keep the stones exposed. Researchers study radioactive isotopes and the chemistry of successive layers to reconstruct how the surrounding ocean changed as each nodule grew. A single object can therefore preserve evidence of shifting oxygen levels, metal supplies, and sediment conditions across ages that saw climates change and species appear or vanish. To your hand, it would feel like nothing more than a rough stone, yet its surface may represent a span of time longer than the existence of many mountain ranges in their present form. The nodule reminds you that growth does not always announce itself through movement. Some things become immense records of change by adding almost nothing at all, patiently gathering the chemistry of the ocean, one invisible layer at a time. Ancient coral reefs are growing in complete darkness miles below the surface. Far beneath the familiar reefs of warm tropical seas, coral colonies are building pale cities without receiving a single useful ray of sunlight. Deep-sea corals can live from relatively shallow continental margins to depths greater than 10,000 feet, where the water is cold and the surrounding landscape remains dark. Unlike most reef-building tropical corals, many cold water species do not contain photosynthetic algae that provide food from sunlight. Their white appearance is therefore natural, not a sign of bleaching. Each colony is made of small animals called polyps, which extend tentacles into passing currents and capture zooplankton and drifting organic particles. This feeding strategy makes moving water essential. Currents deliver food, remove waste, and help prevent the coral from being smothered by sediment. Hard surfaces such as rocky slopes, seamounts, and old coral skeletons provide places where new larvae can attach. As generations grow and die, their calcium carbonate skeletons remain behind, creating an increasingly complex framework upon which later colonies can settle. Over long periods, these accumulated remains can form mounds and reefs that rise above the seafloor and shelter fish, crabs, brittle stars, sponges, and countless smaller organisms. Some individual deep-sea corals can live for centuries or even millennia, while the reef structures beneath them may record a much longer history of repeated growth. Their pace is slow, sometimes only millimeters each year, making large formations the products of extraordinary patience. That slow construction also makes them vulnerable. A structure assembled over centuries can be broken quickly by bottom contact fishing gear, while warming and acidification may alter the water conditions on which its skeleton depends. In 2024, scientists announced that a vast field of cold-water coral mounds off the southeastern United States covered an area larger than the state of Vermont, revealing how extensive these hidden habitats can become. Their existence overturns the simple picture of a coral reef as a bright garden beneath a tropical sun. Here, animals build architecture from captured food and inherited skeletons, creating a living community where color is unnecessary and daylight contributes nothing directly. The reef grows, not because darkness has been defeated, but because life discovered that a current carrying a few particles can be enough to build a world. The ocean floor moves and shifts like a very slow conveyor belt. The ground beneath an ocean is carrying entire landscapes across the planet, while appearing perfectly still to anything living upon it. The seafloor forms part of enormous rigid tectonic plates that move over the softer, hotter material below them, usually advancing only a few centimeters in a year. That is roughly comparable to the rate at which your fingernails grow, yet over millions of years the motion becomes powerful enough to transport underwater mountains, sediments, islands, and sections of ocean basin across thousands of kilometers. The conveyor belt comparison is useful but incomplete. There is no single belt moving in one direction, and the crust does not simply float passively on a circulating river of molten rock. Earth's plates move in different directions and interact along complicated boundaries, driven by forces that include the pull of cold sinking slabs, gravity acting on elevated ridges, and motion within the mantle. Some plates separate, others converge, and some slide sideways past their neighbors, producing earthquakes where rough edges resist and then suddenly break free. One of the clearest records of this movement is written into the magnetism of seafloor rock. As volcanic rock cools, iron-bearing minerals align with Earth's magnetic field and preserve its direction. Because the planet's magnetic polarity has reversed many times, surveys discovered alternating bands of normal and reverse magnetism arranged in matching patterns on opposite sides of ocean ridges. These zebra-like stripes showed that the crust had been carried outward over time, functioning like a geological recording tape. The ages of seafloor rocks support the same story. Broad patterns reveal motion accumulated across immense spans, even though no person can watch a plate cross an ocean during a lifetime. This movement slowly changes the shapes of basins, redirects currents, shifts islands into new climates, and alters the distances between continents. A location on the seabed is therefore not permanently attached to the coordinates where you find it today. It is a passenger on a moving plate, participating in a journey that began long before the present ocean existed and will continue after its coastlines have been transformed. The floor feels stable because your life is brief compared with its motion. Stretch your sense of time far enough, however, and solid ground begins to behave less like a foundation and more like a page being quietly drawn through the machinery of the Earth. New ocean floor is being created every day at mid-ocean ridges. While the continents seem fixed beneath cities and roads, the planet is quietly manufacturing new ground along a submerged mountain system nearly 65,000 kilometers long. Mid-ocean ridges mark places where tectonic plates separate, reducing pressure on the hot mantle rock below and allowing part of it to melt. This molten material rises through fractures, cools, and becomes fresh oceanic crust. Some hardens beneath the surface as coarse rock, some fills near vertical cracks, and some reaches the seafloor as dark basalt, together constructing a new section of plate from the inside outward. The title does not mean that every point along every ridge erupts each day. Activity is uneven, and a particular section may remain quiet for years before magma enters it again. Across the entire global ridge system, however, Crust formation is an ongoing planetary process, continuing somewhere even while no one observes it. Ridges also differ according to how rapidly their plates separate. Fast-spreading ridges tend to receive magma more steadily and often develop broad, smoother crests, while slow-spreading ridges can form rugged valleys where faulting plays a greater role in pulling the crust apart. Newly formed rock begins hot and relatively buoyant, so it stands higher near the ridge. As it travels away, it cools, contracts, and sinks deeper, causing ocean basins to become progressively lower with distance from their birthplace. Sediment then begins covering the exposed basalt, first as a thin dusting and eventually as a much thicker record of time. This means that every piece of ordinary ocean floor has an age and a direction of travel. It was born at a spreading boundary carried outward and slowly changed from warm young crust into a colder, denser plate. You may think of creation as a rare event belonging to the distant formation of Earth, but the seafloor reveals a planet still under construction. New land is not always raised into sunlight where people can name it. Much of it begins unseen, glowing briefly beneath cold water before joining the dark foundation of an ocean. Old ocean floor is being pulled back into the Earth at subduction zones. No ocean floor is promised permanence, because the same planet that creates new crust must eventually make room by consuming the old. This happens at subduction zones, where tectonic plates converge and a cold, dense oceanic plate bends downward beneath another plate. The descent often begins beside a deep trench, where the seafloor curves into the Earth like the edge of a vast sheet being drawn beneath a surface. Gravity acting on the sinking slab helps pull the rest of the plate behind it, making slab pull one of the strongest forces driving plate motion. The process is slow enough to seem motionless, commonly advancing only a few centimeters each year, yet it can carry an entire ocean basin into the mantle over geological time. The descending plate does not simply melt the moment it crosses beneath another. It can remain a recognizable solid slab for hundreds of kilometers, while heat and pressure gradually transform its minerals. Water stored within altered rock and sediment is released during this descent, entering the mantle above and helping some of that overlying material melt. The resulting magma may eventually rise to feed chains of volcanoes far inland from the trench. Meanwhile, the boundary between the plates can lock for decades or centuries as stress accumulates. When it finally slips, the movement may produce some of the largest earthquakes on Earth and, if the seafloor is displaced, destructive tsunamis. Not everything riding on the plate completes the same journey. Sediments may be scraped off and piled against the upper plate, while underwater mountains can become crushed, fragmented, or attached to a continental margin. Still, most ancient oceanic crust has disappeared through this recycling system. The ocean floor present today has an average age of only about 55 million years. And its oldest large regions are roughly 180 million years old, remarkably young beside continental rocks measured in billions of years. The deep past of vanished oceans has therefore been physically carried away, leaving only fragments preserved in mountains and rare pieces stranded on land. Subduction shows you that destruction and renewal are not opposite processes in geology. They are connected parts of one cycle. The ground sinks, changes, releases water, contributes to new magma, and loses its former identity, returning material to the Earth from which another surface may eventually emerge. The deepest parts of the ocean are called hadal zones, after the Greek underworld. The ocean reserves the name of the Greek underworld for its deepest places, but the hadal zone is not one continuous kingdom spread evenly beneath every sea. Named after Hades, it generally begins around 6,000 meters below the surface and extends into trenches approaching 11,000 meters deep. Most ordinary deep sea floor lies above this range, so hadal environments occur mainly inside long, narrow trenches, troughs, and other depressions scattered across the globe. Together, they cover an area roughly comparable to Australia, yet they remain separated from one another by shallower abyssal plains, making each trench something like a remote island turned downward into the Earth. Their steep sides can funnel sinking particles and disturbed sediment toward the bottom, causing organic material to gather unevenly rather than simply decreasing with depth. Earthquakes may trigger landslides that suddenly carry fresh sediment into the trench, burying older surfaces and reshaping habitats in a matter of hours. This creates a more varied environment than the old image of a flat, empty graveyard. Amphipods, sea cucumbers, microbes, worms, and specially adapted fishes inhabit different parts of these trenches. Although the deepest known fishes disappear before the absolute bottom is reached, suggesting that even adaptation has physical limits. The isolation of individual trenches may also restrict movement between populations, allowing related animals in different hadal regions to develop along separate evolutionary paths. Yet scientists still know relatively little about how connected these communities are, because collecting intact animals and recording natural behavior at such depths remains exceptionally difficult. The word hadal can therefore mislead you if it makes the region sound like a single lifeless abyss. It is better understood as an archipelago of depth, multiple enclosed worlds shaped by different geology, food supplies, and histories. Hades was imagined as a final destination beneath the world of the living, but the real Hadal Zone is not an ending. It is a collection of habitats where matter continues to move, organisms continue to adapt, and life occupies spaces that human language once reserved for the dead. The Mariana Trench is deep enough to submerge Mount Everest with miles to spare. Lower Mount Everest into Challenger Deep, and its famous summit would disappear beneath more than 2 kilometers of seawater. The deepest reliably measured point of the Mariana Trench lies about 10,935 meters below mean sea level, while Everest rises about 8,849 meters above it. That leaves more than 2,000 meters, or roughly 1 1/3 miles, between the mountain summit and the ocean surface, so the familiar phrase "miles to spare" is slightly exaggerated in the plural, but still captures an astonishing scale. Yet the comparison can also mislead you, because the trench is not a giant vertical hole shaped perfectly to hold a mountain. It is a long, curved depression created where the Pacific Plate bends beneath the smaller Mariana Plate, with steep slopes descending towards several elongated basins. Challenger Deep itself contains multiple low areas rather than one simple pit, and measuring their exact depths is remarkably difficult. Sound waves used by ships must travel through nearly 11 kilometers of water whose temperature, pressure and salinity alter their speed, while the motion of the vessel and the shape of the seafloor introduce further uncertainty. Modern crude dives have therefore combined pressure measurements, acoustic instruments, gravity corrections, and careful estimates of sea level to refine the number. Even a difference of a few meters matters when scientists are identifying the lowest natural point on Earth. The trench's size also changes how you think about mountains. Everest feels enormous because it rises into air where you can see its outline. Divide it into camps and imagine a path toward the summit. Challenger Deep hides its scale inside water, offering no distant view that allows the eye to understand the descent. A submersible traveling downward may spend hours surrounded by water without any visible reference point, crossing a vertical distance greater than the height at which commercial aircraft commonly cruise. The mountain comparison is therefore useful not because Everest truly belongs there, but because it gives your land-shaped imagination something solid to place inside an otherwise invisible depth. Even then, the picture remains incomplete. The trench would not merely cover the world's highest summit. It would place that summit beneath a final layer of water deep enough to contain another mountain of its own. The ocean floor at the deepest points is completely flat and featureless. The bottom of the deepest ocean may appear like a dim plane beneath a submersible's lights, but calling it completely flat and featureless erases the violent geology written into the ground. Challenger Deep is composed of several elongated basins surrounded by enormous slopes, faulted crust, collapsed sediment, and structures produced as one tectonic plate bends toward the mantle. Within the lowest basins, fine material can settle into depressions, and create locally smooth expanses of soft sediment, which helps explain why early observers described parts of the bottom as flat. A camera hovering only a few meters above such a patch may show little more than pale mud, marked by scattered tracks and small organisms. At that narrow scale, the landscape can seem almost empty. Wider and more precise maps reveal something very different. The deepest area contains separate eastern, central, and western depressions, each several kilometers long, arranged in a stepped pattern along the trench axis. Beyond them rise steep walls shaped by faulting, slope failure, and the deformation of the descending plate. Earthquakes can loosen material from these slopes and send sediment rushing downward, producing deposits that bury older surfaces and subtly reshape the floor. Even the apparently smooth mud contains structure. Ripples, cracks, burrows, feeding trails, fragments of rock, and layers delivered by events occurring far above or along the trench walls. The illusion of featurelessness also comes from the limitations of artificial light. A submersible illuminates only a small circle, while mountains and slopes beyond that circle remain hidden in darkness. It is like standing in a desert at night with a flashlight pointed at your feet and concluding that the entire landscape is a flat patch of sand. Sonar provides the wider view, but its resolution decreases across such extreme distances, meaning that smaller features can remain invisible even on sophisticated maps. The title is therefore best understood as a myth born from scale. Some of the lowest patches are relatively level because gravity carries loose sediment into the deepest available spaces, but the trench as a whole is a complex tectonic landscape rather than a smooth bowl. At the very bottom of Earth, flatness and violence coexist. The local surface may look calm, while beneath it a plate is bending, faults are accumulating strain, and the architecture of the basin continues to be shaped by forces powerful enough to move continents. Brine pools on the ocean floor are so dense that objects float on their surface. There are places on the seafloor where an object can sink through ordinary seawater, reach what looks like another liquid surface, and suddenly stop as though it has landed on an invisible floor. This happens because the water inside a brine pool contains far more dissolved salt than the ocean around it, giving it much greater density. Any object or parcel of water less dense than the brine may remain at the boundary or float upon it, just as wood floats on ordinary water, although whether a particular object stays there depends on its own density, shape, and momentum. The boundary can be sharp enough to form visible ripples and slow waves when disturbed, creating the uncanny appearance of a lake hidden inside another body of water. In regions such as the Gulf of Mexico, thick deposits of ancient salt lie buried beneath younger sediments. Over geological time, this salt can deform and rise because it behaves differently from the surrounding rock. Seawater entering cracks may dissolve part of it, producing concentrated brine that escapes onto the seabed and flows downhill. Since the brine resists mixing and remains heavier than normal seawater, it collects in depressions, sometimes forming channels, waterfalls, and pools with shore-like margins. The interface between the two waters is called a halocline, a zone where salinity changes rapidly across a short distance. Light bends differently through the layers, which can make the surface shimmer like heated air above a road. A remotely operated vehicle approaching the boundary may stir it with its thrusters, sending slow folds across the pool, or briefly pushing ordinary seawater downward before buoyancy returns it upward. Sediment carried by the brine may also move along the bottom, like a dense underwater river, showing that the pool is not necessarily motionless even when its surface appears calm. The strangest part is that nothing solid separates the two liquids. Their boundary exists because gravity continually sorts them according to density, keeping the heavier solution below and the lighter ocean water above. Mix them vigorously enough and the distinction weakens, but left undisturbed, the layers rebuild themselves. These pools show that a surface does not require air on one side and water on the other. It requires only two fluids that resist becoming one, allowing an ocean to contain its own shorelines, waves, and floating objects without ever leaving the sea. we have better maps of the moon than of the ocean floor. You can study the shape of a crater on the moon from nearly 400,000 kilometers away, yet enormous parts of Earth's own seabed remain known only through broad estimates. The familiar claim that we have better maps of the moon is generally true when comparing complete, directly measured topography, although the word better depends on the resolution and type of map being discussed. Lunar orbiters can repeatedly photograph and measure the moon's exposed surface because there is no ocean hiding it. NASA's Lunar Reconnaissance Orbiter has produced near-global elevation models and imagery, with much of the surface photographed at resolutions fine enough to reveal small geological features. Mapping the seabed is slower because ordinary cameras cannot see through kilometers of water, and satellite radar cannot directly measure the bottom. Satellites infer broad underwater shapes by detecting tiny variations in sea surface height caused by gravity, but detailed bathymetry requires ships to cross the ocean while multi-beam sonar sends sound downward in overlapping strips. A vessel maps only the corridor beneath and beside its route, so covering the global seafloor demands years of ship time, fuel, trained crews, and repeated surveys. As of April 2026, only about 28.7% of the world's ocean floor had been mapped to the modern standards used by the Seabed 2030 project. Even mapped areas differ in quality because an old survey made with widely spaced soundings cannot reveal the same detail as a modern multi-beam system. This missing information matters far beyond curiosity. Precise seabed maps help scientists understand tectonic faults, model tsunamis, plan submarine cables, guide research vehicles, study ocean circulation, and identify habitats shaped by underwater terrain. The paradox is not that humanity cares more about the moon than Earth. It is that distance through empty space can be easier to overcome than depth beneath water. The moon reflects light freely toward our instruments, while our own planet conceals most of its landscape beneath a moving layer that absorbs vision and demands that every detailed line be measured from almost directly above. You live on a world whose hidden geography is still being drawn, one slow ribbon at a time. Only a handful of people have ever reached the deepest point of the ocean. For more than half a century, the deepest point on Earth had received only 3 human visitors, making it one of the most exclusive destinations in the history of exploration. Jacques Piccard and Don Walsh reached Challenger Deep in 1960 inside the bathyscaphe Trieste, descending through hours of darkness before settling onto the bottom. No human returned for 52 years until James Cameron completed the first solo descent in 2012. At that moment, the phrase "only a handful" was literally accurate. The number began rising after 2019, when the reusable submersible limiting factor demonstrated that repeated dives to full ocean depth were possible. Scientists, engineers, explorers, and former astronauts followed, and by 2022 the total number of individuals known to have reached Challenger Deep had grown to 27. Published accounts through 2025 continued to cite that figure, so the group remains tiny by any reasonable comparison, but it is no longer merely 3 or 4 people. Reaching the bottom requires far more than allowing a vessel to sink. The crew must remain inside a pressure sphere built without a weakness that could fail under the weight of almost 11 kilometers of water. The craft needs independent life support, batteries, navigation systems that function without satellite signals, and ballast capable of being released so the vehicle can return even after electrical failure. Communication with the support ship is slow and limited, while the pilots navigate through darkness using sonar instruments and carefully planned descent coordinates. Once they arrive, the visible world may extend only as far as the submersible's lights, turning the lowest place on Earth into a small illuminated circle surrounded by unseen terrain. Each visitor therefore reaches a geographic extreme without experiencing it as a grand panorama. There is no horizon to admire and no summit from which to look back. There is only sediment, instruments, the quiet interior of the cabin, and the knowledge that the entire ocean is stacked overhead. 27 people may be more than a handful in the strictest sense, but against the billions who have lived on Earth, it remains a nearly vanishing number. Humanity has inhabited the planet for thousands of generations, yet almost no one has personally touched the lowest boundary of the world that carried them. More people have been to the moon than to the bottom of the Mariana Trench. For decades, this comparison was true, repeated because it captured something almost unbelievable. Humanity had sent more people toward the moon than to the deepest point of its own ocean. 12 astronauts walked on the lunar surface during the Apollo missions, while 24 humans in total traveled to the moon or entered its vicinity during crewed Apollo flights. By contrast, only Jacques Piccard, Don Walsh, and James Cameron had reached Challenger Deep before the new generation of full-depth expeditions began in 2019. The comparison changed soon afterward. By June 2020, 13 individuals had already visited Challenger Deep, exceeding the number who had walked on the moon. And by 2022, the total had reached 27, surpassing even the 24 people who traveled to the moon. The title is therefore historically powerful, but no longer factually current. What makes the reversal fascinating is that the moon did not become easier to reach. The deepest ocean became repeatable. The Apollo program used enormous rockets, global tracking systems, and the resources of a national space effort, while the early journeys into Challenger Deep depended on rare experimental craft that could not easily be reused. Trieste made one historic descent there, and Cameron's deep-sea Challenger also completed a singular human visit. The arrival of limiting factor, designed for repeated dives to any ocean depth, changed exploration from isolated achievement into a sequence of missions. Yet numbers alone can distort the comparison. Lunar astronauts traveled hundreds of thousands of kilometers and operated in a vacuum, while deep-sea crews remain geographically close to Earth's surface but face pressure that can destroy a flawed vessel in an instant. Space offers long-distance communication through radio, while seawater severely restricts it. The moon can be observed from afar before landing, but the trench bottom remains hidden until a vehicle is nearly upon it. These are not competing achievements. They are different confrontations with environments hostile to the human body. The old comparison still teaches something valuable, but not the lesson it once did. It shows how quickly an apparently permanent fact can become outdated when engineering changes what is repeatable. Exploration is not measured only by how distant a destination appears. Sometimes the harder frontier is the one lying directly beneath your own world, waiting not for a stronger telescope, but for a machine capable of surviving the weight of home. The Titanic has been slowly dissolving on the ocean floor for over a century. The Titanic is not resting beneath the Atlantic as a perfectly preserved ship. It is being returned to the ocean one weakened fragment at a time. Since sinking on April 15, 1912, its iron hull has remained exposed to cold salt water, dissolved oxygen, ocean currents, chemical corrosion, and communities of microorganisms that colonize metal. Some of the most visible signs of this process are rusticles, fragile formations that hang from the wreck like reddish-brown icicles. They are not ordinary rust alone, but complex microbial communities living within porous structures made partly from iron compounds removed from the ship. As corrosion continues, solid metal is transformed into weaker material that can crumble when disturbed or eventually collapse under its own weight. This does not happen evenly. Thick plates, steel fittings, brass objects, and protected interior spaces decay at different rates, while sections already damaged during the sinking are especially vulnerable. When the wreck was found in 1985, at a depth of about 3,800 meters, its bow still retained many recognizable features, but repeated surveys have documented railings disappearing, decks weakening, and structures collapsing. During the 2024 expedition, researchers confirmed that a 15-foot section of railing on the port side of the bow had fallen to the seafloor, permanently changing one of the wreck's most familiar outlines. No scientifically reliable date can tell us exactly when the remaining structure will disappear, because corrosion depends on local chemistry, water movement, microbial activity, and the strength of each component. Even after the hull loses its shape, however, Titanic will not simply vanish. Engines, machinery, ceramics, glass, coal, and thousands of objects scattered through the debris field will follow different timelines of decay. The ship is therefore becoming less like a single vessel and more like an archaeological landscape. You may think of a wreck as an event frozen at the moment of sinking, but Titanic reveals that destruction continues long after the last sound fades. The ocean is not merely holding the ship in darkness, it is slowly dismantling human engineering and returning its materials to natural cycles. What remains today is not permanent, which is why careful documentation matters. Every new image is not simply another view of the past, but a record of something the future may never be able to see again. Ancient cities and lost structures have been found beneath the ocean. A road can continue beneath the waves, passing houses, courtyards, tombs, and harbors belonging to people who once believed the shoreline would remain where they knew it. Genuine submerged settlements have been discovered in many parts of the world, but they should not be confused with unsupported stories of Atlantis or mysterious civilizations erased without evidence. Most were drowned through understandable geological and climatic processes. During the Ice Age, enormous volumes of water were locked inside continental ice sheets, leaving global sea level far lower than it is today. For most of human existence, coastlines extended beyond their present positions, and people lived, hunted, traded, and built upon land that later disappeared as the ice melted. Other settlements sank when earthquakes lowered the ground, shorelines eroded, rivers changed course, or tsunamis damaged coastal communities. Pavla Petri in Greece preserves the plan of a Bronze Age settlement beneath shallow water, including streets, buildings, courtyards, and burial structures. Near Egypt, the remains of Thonis Heracleon and Canopus reveal temples, statues, inscriptions, anchors, and harbour installations from cities that once controlled important Mediterranean trade routes. Parts of ancient Alexandria, including remains associated with the area of the Pharos Lighthouse, also lie beneath the sea. In Jamaica, much of Port Royal sank after a devastating earthquake in 1692, leaving sections of a once prosperous colonial town underwater. Archaeologists study these places using sonar, careful diving surveys, photogrammetry, sediment sampling, and remote vehicles capable of recording structures without removing them. Underwater ruins are often difficult to interpret because walls collapse, currents relocate smaller objects, marine growth hides surfaces, and modern construction can damage sites before they are properly documented. Yet submerged settlements offer something land archaeology often cannot. Urban areas that were abandoned suddenly and then protected from generations of rebuilding. Their streets may preserve the arrangement of ordinary homes, workshops, storage areas, and public spaces, revealing how people actually moved through their communities rather than only how rulers described them. These cities were not created to become mysteries. They were once normal places filled with routines, arguments, labor, trade, and expectations of tomorrow. Their presence beneath the water reminds you that coastlines are temporary agreements between land and sea. A city may feel permanent while you inhabit it, but the planet keeps no promise that the ground beneath memory will always remain dry. The ocean floor contains thousands of unexplored shipwrecks. Somewhere beneath an ordinary stretch of ocean, a ship may still be waiting for the first human being to learn where its final voyage ended. UNESCO has long cited estimates of more than 3 million shipwrecks in the world's waters, meaning that the title's thousands may describe only a small fraction of the true number. These wrecks span ancient trading vessels, fishing boats, warships, slave ships, merchant fleets, passenger liners, aircraft, and countless smaller craft that disappeared without precise coordinates. Before modern navigation, crews often knew their positions only approximately, while storms, currents, combat, and navigational errors could carry vessels far from the locations later written in official records. Some ships left no survivors, and others vanished before anyone on land even knew they were in danger. Finding them requires more than searching for a recognizable hull. Researchers begin with port records, insurance documents, naval reports, cargo lists, weather logs, survivor testimony, and old charts, gradually narrowing an area that may still cover hundreds of square kilometers. Side-scan sonar can reveal unusual shapes or shadows on the bottom. Magnetometers can detect disturbances caused by iron, and autonomous vehicles can follow carefully spaced routes without risking human divers. Even then, a promising target may turn out to be a rock, a modern object, or a vessel entirely different from the one being sought. Many wrecks are partly buried, broken into debris fields, or located beyond depths accessible to ordinary diving. Unexplored can therefore mean several things. The wreck has never been found. Its identity remains unknown. Only a sonar image exists, or no archaeological survey has examined the site closely enough to understand it. Publicizing a discovery can also place it in danger, because valuable artifacts may attract looters who remove objects without recording their positions, destroying the relationships that give a site historical meaning. For this reason, exact coordinates are sometimes kept confidential while authorities plan protection and research. A shipwreck is not simply a container of treasure. It may hold evidence of construction methods, migration, warfare, commerce, diet, technology, and the private lives of people otherwise absent from written history. The ocean's unexplored wrecks are therefore not empty legends waiting to enrich whoever finds them first. They are unfinished investigations, each carrying a human story whose final chapter has been present all along, resting silently where no historian has yet been able to read it. Scientists have found microplastics, even in the deepest ocean trenches. The deepest trenches on Earth were once imagined as places too remote to be touched by ordinary human waste. Yet scientists have recovered synthetic fibers and plastic fragments from animals living almost 11 kilometers below the surface. Microplastics are pieces smaller than 5 millimeters, often created as larger objects break apart or released directly from clothing, fishing equipment, industrial materials, paints, and vehicle tires. Researchers examining amphipods from 6 Pacific trenches found synthetic particles inside animals collected at depths between 7,000 and 10,890 meters, including specimens from the Mariana Trench. Separate studies have also detected microplastics in Hadal sediments, showing that the contamination is not merely passing through the water, but becoming buried within the deepest seabed. These particles do not fall in one simple journey. Some become coated with microbes and organic material, increasing their weight, while others are swallowed near the surface and later expelled in denser waste. Powerful sediment flows moving through submarine canyons can also carry plastic rapidly downward, and the steep walls of trenches may guide material toward their lowest basins. Once there, a particle can be eaten by scavengers that have no way to distinguish it from food. Scientists are still studying the consequences because plastic type, size, shape, chemical additives, and the amount consumed all affect biological risk differently. Some particles may pass through an animal, while others can remain inside, interfere with feeding, damage tissues, or carry pollutants attached to their surfaces. The discovery does not mean that every trench animal is visibly filled with plastic, or that all individuals are immediately dying from it. It means something more difficult to dismiss. Even habitats separated from cities by thousands of kilometers and an immense vertical distance are connected to human production. The trench did not create this material, yet its shape may turn it into a final collection point. What sinks out of sight does not leave the planet. It simply enters a world where the consequences become harder for us to observe. Nuclear waste was dumped into the ocean for decades. For 47 years, governments treated parts of the ocean as disposal grounds for radioactive material, trusting depth, distance, and dilution to separate the waste from human life. The first reported sea dumping occurred in 1946, and the practice continued until 1993, with 14 countries using more than 80 known sites. The material was not all identical. Records include packaged low-level and intermediate-level waste, contaminated laboratory and industrial equipment, reactor components, solid containers, and some liquid radioactive waste. Much of it was placed in the North Atlantic and Pacific, while additional dumping occurred in Arctic and other regional seas. At the time, supporters argued that carefully selected deep water sites could disperse relatively low concentrations and keep dangerous materials away from populated land. But the ocean is not a sealed vault. Metal drums can corrode, sediments can move, organisms can interact with released substances, and different radionuclides remain hazardous for very different lengths of time. This does not mean that every historical dumping site became a vast radioactive disaster. Environmental effects depend on what was dumped, how much radioactivity it contained, the condition of its packaging, local currents, depth, chemistry, and whether the material remained concentrated or dispersed. That complexity is precisely why the legacy must be monitored rather than reduced either to panic or reassurance. International attitudes gradually shifted as scientists, governments, and the public questioned whether a shared environment could ethically be used for wastes whose behavior might outlast the institutions responsible for them. Amendments to the London Convention adopted in 1993 and entering into force in 1994 banned the sea dumping of radioactive waste, and international reviews report no new deliberate dumping by participating states since the ban. Yet prohibition does not remove what was already placed below. Some locations are well documented, while the histories of others were reconstructed only after records became available. The containers on the seabed carry more than radioactive material. They preserve an older belief that distance could function as disappearance. The ocean has revealed the flaw in that belief. A substance may be placed beyond the horizon, but responsibility does not become weaker simply because the evidence is difficult to reach. Submarines have heard strange, unexplained sounds from the deep ocean. A sonar operator can hear a rising metallic tone, a distant pulse, or a low vibration crossing the ocean and still have no immediate way to know whether it came from an animal, a machine, moving ice, or the planet itself. Submarines rely heavily on passive sonar, listening without announcing their position, while fixed hydrophone networks record pressure waves traveling through the sea. These systems were developed partly for military surveillance, but their recordings also revealed an acoustic world filled with signals that did not fit familiar categories. Earthquakes create sharp or rumbling arrivals. Volcanoes produce long tremors. Whales repeat recognizable calls. Ships leave mechanical rhythms, and enormous ice masses fracture with enough force to be detected across remarkable distances. The difficulty is that very different events can create surprisingly similar patterns after the sound has traveled through changing water and been altered by distance. One of the most famous recordings, the powerful 1997 sound called the bloop, inspired years of speculation because it was detected by hydrophones separated by thousands of kilometers. Later observations showed that its acoustic signature matched icequakes produced when large Antarctic icebergs cracked and broke apart. Other signals remain less certain. The repeating sound known as upsweep has been recorded since the early 1990s and roughly located near an area of suspected volcanic activity in the South Pacific. But NOAA still describes its exact origin as unresolved. This does not make it evidence of a giant unknown creature. In science, unexplained usually means that the available signal does not contain enough information to identify its source confidently. Researchers compare timing across multiple sensors, examine frequency patterns, locate possible origins, and wait to see whether the sound repeats alongside an earthquake, eruption, animal migration, or ice event. Some mysteries disappear when better instruments are deployed. Others remain as entries in an acoustic archive, carrying too little context for certainty. The ocean does not need monsters to sound alien. A glacier breaking hundreds of kilometers away, a species not yet matched to its call, or rock shifting beneath the seabed, can produce noises no human ear evolved to recognize. Listening below the surface is therefore an exercise in humility. You may detect that something happened long before you understand what kind of event the sound is asking you to imagine. The bloop was a sound so loud it was detected across the entire Pacific. In the summer of 1997, underwater microphones captured a rising sound so powerful that stations separated by thousands of kilometers recorded the same distant event. And for years, its unknown source allowed human imagination to build something enormous beneath the waves. The signal became known as the bloop, a name taken from the strange shape of its sound when played back at a much faster speed. It was recorded by hydrophones that had originally formed part of a Cold War listening network designed to detect submarines across the Pacific. Because low-frequency sound can travel exceptional distances through seawater, several separated instruments were able to hear the event and roughly estimate the region from which it came. The phrase "across the entire Pacific" is dramatic rather than exact, but signals like the bloop can be detected by sensors more than 5,000 kilometers from their source, a range large enough to make one event seem almost ocean-wide. Early descriptions noted that its changing frequency resembled the pattern of a biological call, yet its strength appeared greater than sounds produced by any animal then known. This uncertainty encouraged stories of undiscovered creatures, but the final explanation emerged not from speculation, but from comparison. As NOAA researchers recorded large Antarctic icebergs cracking, grinding, and breaking apart, they discovered icequakes with acoustic patterns remarkably similar to the bloop. A massive sheet of ice under stress can fracture across an enormous area, forcing energy into the surrounding water and creating a sound capable of traveling far beyond the visible event. The original recording was also played at about 16 times its natural speed for public listening. At its real pace, it would have sounded much lower, slower, and less like the sudden vocalization people often imagine. The bloop was therefore not the cry of a hidden giant, but that does not make it ordinary. It was the sound of part of the frozen planet breaking, carried through the ocean until machines on distant sides of the Pacific registered the same disturbance. Perhaps the mystery was solved only because scientists learned to compare the ocean with ice rather than life. The lesson is quieter than the legend, but more useful. When nature produces something unfamiliar, the unknown does not automatically point toward a monster. Sometimes it reveals that a familiar part of Earth is powerful enough to sound alive. The ocean absorbs more carbon than all the world's forests combined. Every breath of industrial carbon released into the atmosphere begins a journey, and a remarkable share of it eventually crosses the ocean's surface and becomes part of the chemistry of seawater. The title is difficult to express as a simple permanent rule, because forests are only one part of the land carbon sink, and the strength of both land and ocean uptake changes from year to year. Yet the latest global carbon budget estimates that during the decade from 2015 to 2024, the ocean absorbed about 29% of total human carbon dioxide emissions, while the net land sink absorbed about 21% after accounting for the carbon released through land use change. In that recent net comparison, the ocean did take up more carbon than all land ecosystems combined, not merely forests. Carbon dioxide enters the sea wherever the concentration in the air is higher than in the surface water. Once dissolved, it reacts with water and becomes a mixture of carbon-containing forms, allowing the ocean to hold far more carbon than it could if the gas simply remained unchanged between water molecules. Winds, mixing, and circulation then move some of that carbon away from the surface, allowing more atmospheric carbon dioxide to enter. The ocean already contains an immense natural carbon reservoir, estimated to be many times larger than the amount stored in the atmosphere or in terrestrial plants and soils. This buffering capacity has slowed the growth of atmospheric carbon dioxide and therefore reduced some of the warming humanity would otherwise have experienced. But absorption is not the same as harmless disappearance. The chemical reactions produced by additional carbon dioxide increase the concentration of hydrogen ions and lower seawater pH, a process called ocean acidification. The ocean is not becoming acidic like vinegar, but it is becoming less alkaline. changing the chemical balance used by corals, shell-forming animals, and many microscopic organisms to build calcium carbonate structures. Warming water also holds carbon dioxide less easily, while changes in winds and circulation can strengthen or weaken regional uptake. The latest assessment indicates that the ocean sink has been relatively stagnant since 2016 and has been affected by recent climate variability and marine heat. This means the sea should not be imagined as an endless container waiting to solve the problem created above it. It is absorbing part of our emissions by changing itself. The carbon has not vanished. It has crossed a boundary, entered living and chemical systems, and altered the conditions within them. What looks like rescue from the atmosphere is also a debt being quietly transferred into the water, reminding you that the planet can soften the consequences of human action without making those consequences disappear. The deep ocean is one of the last places on Earth almost untouched by humans. Camera can descend into a deep valley that no person has ever visited and still find a plastic bag resting beside an animal that has never seen the surface. This is the contradiction at the heart of the idea that the deep ocean remains almost untouched. In a direct physical sense, much of it has never been entered, photographed, sampled, or disturbed by machinery. Humans have visually observed less than 1,000th of 1% of the deep seafloor, leaving immense regions where no ship has dragged equipment, no submersible has landed, and no artificial light has passed across the bottom. Yet isolation from human bodies is not the same as freedom from human influence. Greenhouse gases have warmed the ocean from the surface into deeper layers, altered its chemistry, and reduced oxygen availability in many regions. The IPCC concludes that marine life from polar seas to abyssal depths is already experiencing effects of human-driven climate change, even where the temperature shift is small enough to escape casual detection. Debris also reaches places far beyond cities and shipping lanes. During surveys of the Western and Central Pacific, researchers found metal, glass, plastic, rubber, cloth, fishing gear, ammunition, and other human-made objects during more than 17% of the deep dives they reviewed, at depths reaching 6,000 meters. Some corals were entangled in lines, while other animals used bottles and discarded objects as shelter or attachment surfaces, demonstrating that pollution can become part of an ecosystem without becoming natural. Commercial fishing has scraped sections of the seabed. Lost gear continues catching animals after its owners disappear. Underwater noise travels beyond its source, and pollutants can move through currents and food webs into places no human has personally reached. The phrase "almost untouched" is therefore best reserved for landscapes that remain physically unvisited, not environments sealed from our civilization. The deep sea may be the last great wilderness in the geography of human exploration, but it is not outside the atmosphere, climate, chemistry, or waste system of the planet. This distinction matters because believing a place is untouched can make its protection seem less urgent, as though distance itself were already guarding it. In reality, the deep ocean receives consequences long before it receives witnesses. Humanity has developed the power to alter environments it has not yet learned to describe, creating a strange new form of presence. We arrive through heat, carbon, noise, and debris before our eyes ever reach the scene. The deepest wilderness is still unknown to us, but it can no longer be called completely beyond us. Remote control vehicles have only explored a tiny fraction of the ocean floor. Every time a remotely operated vehicle descends, it enters an area so vast that its brightest lights reveal little more than a moving keyhole in a locked world. An ROV is connected to a research vessel by a long tether carrying electrical power, commands, and high-definition video between the machine and pilots at the surface. Thrusters allow it to hover over cliffs, approach delicate organisms, collect samples with robotic arms, and remain below much longer than a human diver could survive. Yet these abilities do not make exploration fast. A deep dive may require hours of descent before the vehicle even reaches its target, and once there, it usually travels slowly so scientists can examine the terrain without colliding with rocks, stirring sediment, or overlooking small animals. Its cameras illuminate only a narrow corridor, leaving everything beyond the lights unrecorded. The support ship must follow above. The tether must be kept clear of obstacles. Weather can end operations. And every day at sea requires a large crew and specialized equipment. A 2025 study estimating all known deep-sea visual observations since 1958 concluded that humanity has directly imaged less than 1/1000% of the deep-sea floor. That figure includes footage from ROVs and other deep-sea vehicles, making the fraction explored by remote-controlled machines alone smaller still. The observations are also geographically uneven. A large share has occurred near a few technologically wealthy countries. So much of what scientists call typical deep-sea life may be based on places that were convenient to reach, rather than places that fairly represent the whole ocean. Even previously visited sites remain only partly understood because one pass cannot reveal seasonal changes, migrations, reproduction, or rare events. An ROV dive is therefore not like completing a section of a map and permanently crossing it off. It is more like opening one window for a few hours and trying to understand an entire country from what passes outside. These machines have transformed ocean science, but their greatest lesson may be the scale of what they have not yet shown us. Each kilometer of video feels like progress, while the surrounding darkness reminds you that exploration can advance for generations and still remain almost at its beginning. Scientists discover new species in the deep ocean every time they look. A deep-sea expedition can return with animals so unfamiliar that scientists may need years merely to determine where they belong on the tree of life. The phrase, "every time they look," should not be taken literally, because some dives revisit known habitats without finding a new species. But focused expeditions into poorly sampled regions regularly collect organisms that have never been scientifically described. In May 2026, Ocean Census reported that its collaborating researchers had identified 1,121 previously unknown marine species, including a deep-sea ghost shark, corals, crustaceans, worms, anemones, and other animals collected from depths reaching more than 6.5 kilometers. Discovery, however, does not happen at the instant a camera records something strange. A creature may look unusual because it is a known species seen at a new life stage, damaged during collection, or living far outside its previously recorded range. To establish a new species, taxonomists must preserve specimens, study their anatomy, compare them with museum collections and scientific descriptions, analyze genetic material when possible, and identify features that consistently separate them from their closest relatives. The specimen then needs a formal name, a published description, and a designated reference individual that future researchers can examine. This careful process explains why hundreds of candidate species can remain unnamed for years after an expedition ends. It also reveals why the shortage of taxonomic experts can be as limiting as the shortage of research ships. Collecting an animal is only the beginning. Understanding what it is requires knowledge built across generations. The deep ocean produces so many surprises partly because its habitats are physically separated. Trenches, seamounts, canyons, continental slopes, and isolated water masses can restrict movement, allowing populations to evolve independently. Some species may occupy a single ridge or one narrow depth range, making them easy to miss and vulnerable to disturbance before anyone realizes they exist. Others are visually almost identical to known animals but genetically distinct, hiding new biodiversity behind familiar shapes. The excitement of discovery should therefore carry a quiet warning. Humanity is not simply finding strange creatures in an empty catalogue. It is learning that the catalogue itself remains unfinished. An animal can perform its ecological role for millions of years without a human name, and it may disappear without science ever knowing that a unique form of life was lost. Every serious expedition does not guarantee a new species, but each journey into an unsampled habitat increases the chance that the ocean will reveal how little our classifications contain. The ocean. may contain more undiscovered species than all land combined. The most dramatic estimates of hidden ocean life invite you to imagine more unnamed species beneath the waves than across every forest, desert, cave, and mountain on land. But current evidence does not allow that claim to be stated as fact. One influential global analysis estimated that Earth contains about 8.7 million eukaryotic species, meaning organisms whose cells contain a nucleus, with roughly 6.5 million species associated with land and about 2.2 million living in the ocean. The same study suggested that approximately 91% of marine species remained undescribed, leaving close to 2 million ocean species still unknown to science. That is an astonishing number, but under this model, the estimated unknown diversity on land would still be greater because the predicted terrestrial total is much larger. Other studies have produced different marine estimates, sometimes far lower, because counting species that have not yet been found requires scientists to extrapolate from incomplete records. The uncertainty grows when microorganisms are included. Many microbes cannot be classified neatly through appearance, exchange genes in ways that complicate boundaries, and may be known only from fragments of environmental DNA collected from water or sediment. Even among animals, two populations that look identical may prove genetically distinct, while organisms that appear very different can sometimes belong to a single variable species. The word species is therefore a scientific tool rather than a perfectly universal box, and different methods can produce different totals. The ocean may still contain entire groups with almost no described representatives, particularly among tiny worms, crustaceans, parasites, gelatinous animals, and organisms living inside sediment or other bodies. Its enormous volume and fragmented habitats make hidden diversity plausible, but size alone does not guarantee more species. Land environments contain extraordinary variety in temperature, elevation, moisture, vegetation, soil, and host relationships, especially among insects, fungi, and parasites. The honest conclusion is more interesting than the exaggerated title. The ocean probably contains an immense number of undiscovered species, perhaps millions, but science cannot currently show that this number exceeds all unknown land species combined. What the estimates truly expose is not which realm wins a contest of abundance, but how incomplete humanity's inventory of life remains. You inhabit a planet where most species may still have no scientific name, and the question is not merely how many are waiting to be found, but how many may vanish while we are still trying to count them. The deep ocean is in permanent darkness below 200 meters. At 200 meters, daylight does not suddenly switch off, but the ocean begins to erase the sun so thoroughly that life can no longer depend on it in the familiar way. This depth marks the approximate beginning of the mesopelagic, often called the twilight zone, where only a faint and rapidly weakening trace of sunlight remains. The exact boundary changes with water clarity, season, latitude, and the amount of plankton or sediment above, so the title should not be understood as a perfectly fixed line of total darkness. In clear open water, dim blue light may reach several hundred meters deeper, but it is already too weak below roughly 200 meters to support meaningful photosynthesis. Plants and algae cannot build an ecosystem there by capturing sunlight as they do near the surface. As you descend, colors disappear in sequence because water absorbs different wavelengths at different rates. Red fades first, then orange and yellow, while blue penetrates farthest before it too becomes undetectable. By around 1,000 meters, the ocean enters a region of permanent natural darkness where sunlight never reaches, regardless of whether it is noon, midnight, summer, or winter above. This loss of light changes more than visibility. It removes the daily cues that organize much of surface life, forces animals to rely on other information, and turns upward migration into a carefully timed journey between danger and food. Many organisms rise toward shallower water after sunset, feed under the protection of night, and descend before morning restores the light. This movement, performed by countless small animals, is considered the largest daily migration on Earth by biomass. The boundary near 200 meters is therefore not the beginning of absolute blackness, but the beginning of a long transition away from the sun's control. Below it, daylight becomes less useful with every meter, until it survives only as a distant physical fact rather than an experienced part of life. You may think darkness begins when the eye can no longer see, but the ocean reveals a slower truth. A world can lose the sun gradually, layer by layer, until an entire population lives beneath a sky it will never encounter. There are 3 distinct layers of the ocean, with completely different conditions. The ocean may look like one continuous body of water, yet a descent through it can feel like passing through 3 separate worlds stacked invisibly upon one another. Oceanographers often describe its broad physical structure as the surface mixed layer, the transition layer, and the deep layer. The surface mixed layer is continually stirred by wind, waves, and changing weather, which keeps its temperature and many of its chemical properties relatively uniform from top to bottom. It is directly connected to the atmosphere, so gases such as oxygen and carbon dioxide can cross the surface, storms can rearrange it quickly, and seasonal heating can change its depth. Beneath it lies a transition region where conditions shift much more rapidly. Temperature usually falls, density increases, and in some places oxygen, salinity, and nutrient concentrations also change strongly across a relatively short vertical distance. This middle region can separate organisms adapted to warm upper water from those suited to colder depths, while also slowing the exchange of material between the layers. Farther down is the deep ocean, which contains most of the sea's volume. Its water is generally cold, dense, and far more stable than the surface, with temperatures that may change only slightly across enormous distances. It is not completely motionless, however. Deep water masses form in certain high-latitude regions, sink, and travel through ocean basins while carrying distinctive combinations of temperature, salinity, oxygen, and dissolved nutrients. Scientists can identify these water masses almost like fingerprints and follow their paths across the globe. The 3-layer model is a simplification rather than a universal rule. Polar oceans, shallow coastal seas, seasonal conditions, and powerful currents can weaken, strengthen, or rearrange the structure. Biological zones are also often divided into 5 or more depth ranges. So the 3 layers refer mainly to large-scale physical organization rather than every ecological boundary. Still, the model reveals why the ocean cannot be understood as a giant container filled with identical water. A molecule near the surface may experience wind, rapid temperature change, and direct contact with the atmosphere, while another far below may travel for centuries without returning upward. The sea is connected, but it is not uniform. Its layers touch one another constantly while preserving different histories, reminding you that 2 places can occupy the same vertical column and still belong to almost entirely different worlds. The thermocline is a hidden barrier between warm and cold ocean water. You could swim downward through pleasant water and suddenly feel the temperature collapse across only a few meters, as though you had crossed an invisible wall. This rapidly changing region is called the thermocline, a layer in which temperature decreases much faster with depth than it does in the water above or below. Sunlight warms the surface, while deeper water remains cold and dense, and the contrast between them creates a stable vertical arrangement. Warm water tends to remain above cold water, so the thermocline resists ordinary mixing, even though no solid boundary separates the layers. Calling it a barrier is therefore useful, but it is not absolute. Strong storms, seasonal cooling, tides, currents, and internal waves can bend, weaken, deepen, or temporarily break it apart. In many tropical oceans, a permanent thermocline remains present throughout the year because surface heating is consistent. In temperate regions, a seasonal thermocline often develops during spring and summer, then weakens in autumn as the surface cools and winds mix the water more deeply. Polar seas may have little conventional thermocline because the surface is already cold, although changes in salinity can create a different kind of density boundary. The thermocline influences life because it controls how easily nutrients and gases move vertically. Surface organisms may consume available nutrients faster than they are replaced, while colder water below can hold a larger reserve. When wind or currents lift deep water upward, nutrients cross the boundary and can fuel intense biological growth. The layer also shapes where fish gather, how predators search, and how marine animals choose depths that balance temperature, oxygen, and food. Submariners and oceanographers monitor it because changes in water temperature affect buoyancy, visibility, and the way the environment is sensed. Yet its greatest importance may be planetary. By slowing exchange between surface and deep water, the thermocline helps regulate how heat absorbed by the ocean is distributed and how quickly deeper layers respond to atmospheric change. It is not simply a line between warm and cold water, but a moving gate controlling the passage of energy and matter through the sea. You cannot see it from a ship, and a calm surface gives no warning that it exists. But beneath you, the ocean may be divided by a boundary strong enough to organize ecosystems and influence climate without ever becoming a physical wall. Sound travels nearly 5 times faster through water than through air. A distant sound beneath the sea can arrive far sooner than your instincts would ever predict. Because water carries vibration at roughly 1,500 meters per second, more than 4 times the usual speed of sound in air, and close enough to inspire the familiar phrase, nearly 5 times faster. The reason is not simply that water molecules sit closer together. Sound is a moving pattern of pressure, and liquid water strongly resists being compressed, allowing each disturbance to transfer efficiently into the next region of water. Air is easier to squeeze, so part of the motion is spent compressing and expanding the gas before the pressure wave continues. The exact speed underwater is not constant. Warmer water generally carries sound faster. Additional salt increases the speed slightly, and rising pressure at greater depths also has an effect. Oceanographers can therefore measure sound speed to learn about the water itself, while sonar systems must correct for changing conditions or risk placing an object at the wrong depth or distance. Speed does not guarantee perfect clarity, however. High-pitched sounds are absorbed more rapidly. Currents and temperature boundaries can bend sound away from a receiver, and reflections from the surface or seabed may create confusing echoes. Human hearing also becomes strangely unreliable underwater. Because sound crosses the small distance between your ears so quickly, your brain receives less timing difference than it expects and struggles to determine the direction of the source. A boat engine may seem to come from everywhere, even while its sound is reaching you with extraordinary efficiency. This reveals an important distinction. Sound can travel faster without becoming easier for you to understand. The ocean delivers vibration according to its own physical rules, but your senses were tuned for air. Beneath the surface, even something as familiar as a voice enters a medium where speed increases. Direction becomes uncertain, and the world you hear no longer matches the world your brain was built to imagine. The ocean has a natural channel that carries sound around the entire planet. A low pulse released in the right part of the ocean can cross distances so enormous that listening stations on another side of an ocean basin may record an event they could never see. The natural pathway responsible is commonly called the deep sound channel or SOFAR channel, but the claim that it carries sound around the entire planet requires careful interpretation. Continents interrupt the oceans, underwater ridges can block or scatter signals, and no single sound is guaranteed to circle Earth without weakening. Yet, low-frequency vibrations entering favorable routes can travel for thousands of kilometers, and connected ocean basins allow global networks of hydrophones to detect events at extraordinary ranges. This ability became strategically important during the 20th century, when underwater listening systems were developed to follow submarines and later adapted for scientific and humanitarian purposes. Special rescue floats were once designed to sink to the channel's depth and release small explosive signals that distant stations could use to estimate the location of people lost at sea. Today, hydrophone networks listen for underwater earthquakes, volcanic eruptions, iceberg breakups, marine mammals, and explosions associated with nuclear testing. Because several stations may receive the same signal at different times, scientists can compare the arrivals and work backward toward the source, transforming the ocean into a planetary-scale instrument. The sound may travel for hours before reaching a sensor, carrying information about an event that ended long before anyone knew it had occurred. Its path is rarely simple. It can curve through water, split into multiple arrivals, interact with islands, and emerge distorted by the journey, requiring analysts to separate the original event from the ocean's influence upon it. In this sense, the channel does not merely transport sound. It preserves a moving record of how that sound crossed the planet. The sea becomes both messenger and editor, carrying a distant disturbance while reshaping its voice. Long before humans built cables or satellites, Earth already possessed a communication system made from water, pressure, and depth, one capable of linking remote places through signals no eye could follow. Water pressure in the deep ocean compresses everything, including air itself. An ordinary pocket of air carried into the deep ocean does not remain an ordinary pocket of air. It shrinks until the space it once occupied is almost gone. Water is only slightly compressible, but gases respond dramatically to increasing pressure because their molecules begin far apart and can be forced much closer together. Near the surface, a balloon may appear full and buoyant. Yet as it descends, the surrounding pressure squeezes its air into a smaller volume. At 1 kilometer below the surface, an ideal pocket of air would occupy only a tiny fraction of its original size, and near the deepest trenches it could be compressed to around 1/1000th of its surface volume if it remained a gas and its temperature did not change greatly. Real conditions are more complicated because gas can dissolve into water, leak through materials, or behave differently under extreme pressure. But the shrinking effect is unmistakable. Scientists often demonstrate it by attaching foam cups or blocks to deep-sea vehicles. The foam contains countless microscopic gas-filled spaces, and when pressure crushes those spaces during descent, a large cup may return permanently reduced to a miniature version of itself. The material has not simply been pushed inward temporarily. Much of its internal structure has collapsed. This creates serious engineering challenges. Air-filled housings can implode, seals can be forced out of place, and buoyant objects may begin sinking as their internal gas volume decreases. Deep ocean instruments are therefore often placed inside strong pressure vessels, or filled with incompressible oil so that outside pressure is balanced rather than resisted by a hollow chamber. Even bubbles released underwater change as they rise, expanding steadily as the pressure above them decreases, sometimes breaking apart or dissolving before reaching the surface. Pressure is therefore not only a force acting on objects from outside, it changes volume, buoyancy, material strength, and the behavior of gases themselves. The deeper you travel, the less room air is permitted to occupy, until something that felt empty and weightless near the surface becomes a compressed reminder that even emptiness has a physical structure the ocean can squeeze. The salt in the ocean would cover all land on Earth, 1 mile deep. Remove every drop of water from the ocean, gather what remains, and you would uncover enough dissolved salt to bury the continents beneath a mineral layer taller than many city buildings, but not a full mile deep. Scientific estimates place the average thickness at more than 500 feet, roughly 166 meters, so the popular 1 mile claim exaggerates the real figure by about 10 times. Even the corrected number is difficult to imagine. An ocean that looks like pure blue water is carrying dissolved material equal to about 3.5% of its weight, though this salt is not simply the table salt in your kitchen. It is a mixture of charged minerals called ions, dominated by sodium and chloride, but also containing magnesium, sulfate, calcium, potassium, and many other substances in smaller amounts. Most began inside rock. Rainwater absorbed carbon dioxide from the air, became slightly acidic, and slowly weathered mountains and soils. Rivers then carried the released ions toward the sea. Additional minerals entered through volcanic activity and reactions between seawater and oceanic crust. Yet the ocean did not simply become saltier without limit. Marine organisms remove some ions to build shells and skeletons. Minerals become trapped in sediment. Sea spray carries material back onto land, and evaporating basins leave enormous salt deposits behind. Over geological time, these processes have created a shifting balance between what enters and what leaves. The salt around you during a swim is therefore part of a planetary circulation older than any coastline you recognize. Some of its ions may once have traveled through a river that no longer exists, passed through the body of an ancient organism, become locked inside stone, and later return to the sea. The exaggerated 1 mile story is unnecessary because the truth is already immense. Beneath the ocean's apparent emptiness lies enough dissolved rock to cover every forest, desert, city, and mountain base beneath a pale mineral world hundreds of feet thick. When you taste seawater, you are not merely tasting the sea. You are tasting continents slowly surrendered to it. The ocean contains gold, but extracting it is not yet possible. There is gold passing through the gills of fish, surrounding ships and touching every coastline on Earth, yet you could process an almost unimaginable quantity of seawater without collecting enough to fill a small ring. Gold enters the ocean when rocks weather. Rivers carry dissolved traces from land. Particles settle from the atmosphere, and hot fluids interact with mineral-rich crust beneath the seabed. Some of it floats as microscopic particles, some becomes attached to organic matter, and some remains dissolved as individual atoms joined to other chemical substances. Because the ocean is so enormous, the total quantity may sound like a hidden fortune, but total abundance is not the same as useful concentration. NOAA cites measurements from parts of the Atlantic and North Pacific containing only about 1 gram of gold for every 100 million metric tons of seawater. At that dilution, the gold in a tanker full of water would be worth far less than the energy, equipment, chemicals, filtering, and maintenance required to recover it. Scientists can isolate and measure gold from seawater in laboratories, so extraction is not physically impossible. The real barrier is economic and practical. No known process can move enough water, separate the gold selectively from vastly more abundant salts, and operate cheaply enough to produce a profit. Any large system would also have to resist corrosion, avoid creating harmful chemical waste, and prevent damage to marine organisms drawn into the machinery. Past inventors repeatedly promised filters, electrical systems, or chemical treatments that would unlock the ocean's treasure. But the calculations always return to the same problem. The valuable atoms are simply too widely scattered. Gold-rich solid deposits do exist in certain marine sediments and mineral structures, but mining those is entirely different from extracting dissolved gold from ordinary seawater. The ocean therefore contains a lesson about value that extends beyond metal. Something can exist almost everywhere and still remain effectively unreachable because it is spread too thinly to gather without spending more than it gives back. The sea is filled with gold, but it does not offer that gold as a treasure chest. It holds it as a whisper, distributing wealth so completely that possession becomes almost meaningless. Deep ocean water is completely invisible to radio signals. Send a phone call, a GPS signal, or an ordinary radio broadcast toward the deep ocean, and the water will silence it long before it reaches the world below. Seawater contains dissolved ions that allow electrical currents to form, making it far more conductive than air. When common radio waves enter this conductive medium, their energy is rapidly absorbed and converted into tiny amounts of heat, causing the signal to weaken exponentially with depth. Higher frequency signals used by mobile phones, Wi-Fi, radar, and satellites are especially poor at penetrating seawater. which is why a submerged submarine cannot simply raise an internal antenna and connect to a satellite through thousands of meters of water. The title, however, is not literally absolute. Extremely low frequency and very low frequency radio waves can penetrate farther than ordinary signals, and navies have used them to send short messages to submarines operating below the surface. These waves require enormous land-based transmitters, carry information very slowly, and generally cannot support rich two-way communication such as voice, images, or continuous data. A submarine may need to approach a shallower depth, trail a long antenna, or release a communication buoy to receive them effectively. For deeper and faster underwater communication, machines usually turn to sound because acoustic waves can travel through seawater far more successfully than radio. Optical systems using blue-green light can transmit data over limited distances in clear water, but scattering, absorption, suspended particles, and the need for careful alignment restrict their reach. This creates an unusual technological isolation. A spacecraft millions of kilometers away may communicate directly with Earth through radio, while a vehicle only a few kilometers beneath a nearby ship can be almost completely cut off from the communication systems that surround modern life. Messages become slower, bandwidth narrows, and the ocean itself acts like a heavy curtain between transmitter and receiver. Deep water is therefore not truly invisible to every radio frequency, but it is opaque enough to force technology to change its language. Descend beneath the surface, and the invisible web connecting cities, aircraft, satellites, and phones begins to disappear, revealing that the world you call permanently connected depends on signals that cannot follow you everywhere. The ocean generates half of all the oxygen on Earth. Half of the oxygen being created on Earth today is produced not by towering forests, but by an almost invisible living system spread across the sunlit surface of the ocean. Microscopic algae, photosynthetic bacteria, seaweeds, and marine plants absorb carbon dioxide and water, use sunlight to build energy-rich organic matter, and release oxygen as a byproduct. Because the ocean covers most of the planet, countless small acts of photosynthesis add up to roughly half of global oxygen production. But this familiar statement needs an important correction. It does not mean that half of the oxygen entering your lungs this morning was freshly delivered from the sea. Earth's atmosphere contains an enormous reservoir of oxygen accumulated over geological time, and oxygen molecules mix through the air rather than remaining above the ecosystem that produced them. Much of the oxygen made in the ocean is also consumed there. Marine animals breathe it, microbes use it while decomposing dead material, and chemical reactions remove it from the water. NOAA therefore notes that the ocean produces about half of Earth's oxygen, while marine life consumes approximately the same amount. For oxygen to accumulate over very long periods, some photosynthetic organic matter must escape complete decomposition and become buried, preventing all of the released oxygen from being immediately used again. This slow imbalance helped transform the early atmosphere and eventually made complex oxygen-breathing life possible. The oxygen-producing ocean is therefore not a simple machine that endlessly pumps fresh air toward land. It is part of a planetary exchange in which oxygen is continually created, consumed, dissolved, released, transported, and recycled. Conditions within that system can change. Warming reduces the amount of oxygen seawater can hold. Stronger layering can limit the replacement of oxygen in deeper regions. And excessive nutrient pollution can cause blooms whose later decay consumes oxygen and creates suffocating zones. A place filled with photosynthetic life can therefore produce abundant oxygen during daylight and still lose oxygen later when that life dies and decomposes. This apparent contradiction reveals why production and availability are not the same thing. The ocean may generate an immense share of the planet's oxygen, yet whether that oxygen remains available depends on the biological and chemical events that follow. When you take a breath, you are participating in a history far larger than the present moment. Ancient photosynthesis built the atmospheric reservoir around you, while modern marine life continues renewing the cycle each day. The ocean does not hand you a separate breath labeled as its own. It quietly helps maintain the planetary conditions under which breathing remains possible at all. Phytoplankton in the ocean produces more oxygen than all rainforests. A rainforest can rise high enough to hide the sky, yet organisms smaller than a grain of dust may collectively match or exceed the oxygen production of all the world's rainforests. Phytoplankton is a broad name for drifting photosynthetic organisms living mainly in waters where sunlight can reach them. The group includes cyanobacteria, diatoms with glass-like shells, dinoflagellates, coccolithophores covered in tiny mineral plates, and many other forms that differ greatly in size and biology. Individually, most are almost invisible. Together, they carry out close to half of the planet's primary production, converting sunlight and carbon dioxide into living material at a scale comparable to all terrestrial vegetation combined. Their power comes not from longevity or size, but from abundance, rapid reproduction, and the immense area of ocean available to them. A large tree may store carbon for centuries, while a phytoplankton cell may live briefly, divide, be eaten, or sink, allowing the same nutrients to pass through many generations in a short period. One particularly important cyanobacterium, Prochlorococcus, is among the most abundant photosynthetic organisms in nutrient-poor open oceans. A single cell contributes almost nothing you could notice, but populations numbering beyond ordinary imagination help support food webs and global chemical cycles. Diatoms can dominate nutrient-rich blooms, multiplying rapidly when light, nitrogen, phosphorus, iron, and suitable water conditions align. Satellites observe these blooms indirectly by measuring changes in ocean color caused by chlorophyll and other pigments, revealing broad green or turquoise patterns where microscopic life has transformed the surface. The claim that phytoplankton produces more oxygen than all rainforests is broadly plausible when discussing gross annual production, but it should not be treated as a permanently measured contest with one exact winner. Rainforest productivity changes with climate, disturbance, age, and season, while ocean productivity shifts with nutrients, temperature, mixing, cloud cover, and currents. Mature rainforests also consume most of the oxygen they produce because trees, animals, fungi, and decomposing organisms use it again. The same is true in the sea, where much phytoplankton oxygen is consumed by respiration and decay. What matters is not that forests have become unimportant, but that visible size is a poor guide to planetary influence. The Amazon attracts attention because you can see its trees from the ground and from space. Phytoplankton can alter the atmosphere while remaining individually hidden in a glass of seawater. Their existence asks you to reconsider what strength looks like in nature. The systems supporting the largest animals and shaping the chemistry of the entire planet may be built not by organisms that dominate the landscape, but by lives so small that thousands could pass before your eyes without being noticed. The ocean has a heartbeat, tidal cycles that affect the entire planet. The moon never touches the ocean, yet coastlines rise and fall in response to its presence as though the planet were breathing under a distant command. Tides are extremely long waves created mainly by differences in the moon's gravitational pull across Earth, with the sun adding a weaker but still important influence. The side of Earth nearer the moon experiences a slightly stronger attraction than Earth's center, while the far side experiences less, producing a stretching effect across the planet. As Earth rotates through this changing gravitational pattern, ocean water moves in recurring cycles of rising and falling. The simple picture of two smooth bulges moving around a perfectly round world is only a starting point. Continents interrupt the flow. Ocean basins have different depths and shapes. Friction slows moving water, and coastlines can concentrate or reduce the tide. Some locations experience 2 high tides and 2 low tides during a lunar day. Others mainly one of each, and many show mixed patterns with unequal heights. In narrow bays or funnel-shaped estuaries, resonance and geography can produce enormous tidal ranges, while nearby enclosed seas may experience only small changes. The sun and moon also change the strength of the cycle. During new and full moons, their tidal influences reinforce one another, producing spring tides with greater differences between high and low water. Around the first and third quarter moons, the forces partially oppose each other, creating the more moderate ranges called neaptides. These movements do far more than shift a line along the beach. Tidal currents carry larvae, sediments, oxygen, nutrients, and food through estuaries and coastal habitats. Intertidal animals must survive repeated exposure to air, heat, cold, waves, and predators as water arrives and withdraws. In deeper regions, tidal flow across rough underwater terrain produces turbulence and internal waves that mix water layers and help move heat and nutrients vertically. Tidal forces also act on the solid earth and atmosphere, although their effects are less visible than the movement of seawater. Over immense spans of time, friction associated with tides transfers rotational energy from Earth to the Moon's orbit. Earth's rotation is gradually slowing, lengthening the average day, while the Moon is slowly moving farther away. NASA estimates that lunar tidal friction has increased the length of Earth's day by an average of about 2.5 milliseconds per century over long periods, although other processes also cause shorter-term changes in rotation. The ocean's heartbeat is therefore not a perfectly regular pulse shared identically by every shore. It is a complex planetary rhythm shaped by gravity, rotation, basin geometry, weather, and the changing positions of three worlds. Every tide quietly connects a small coastal pool to the motion of the Moon, the slowing spin of Earth, and an astronomical relationship that has been evolving for billions of years. The water touching your feet may seem to move only a few meters across the sand, yet the force behind that movement is slowly changing the architecture of time itself. Deep ocean currents circle the globe on a journey that takes over 1,000 years. A drop of water sinking into the North Atlantic today may not return to the surface until civilizations, coastlines, and perhaps the language you speak have changed beyond recognition. This slow movement belongs to the global overturning circulation, often simplified as a great ocean conveyor belt linking surface currents with vast flows in the deep sea. The journey begins most powerfully in a few high-latitude regions where surface water becomes cold and dense enough to sink, carrying dissolved oxygen and traces of the atmosphere into the ocean's interior. Some of this deep water travels southward through the Atlantic, joins currents circling Antarctica, and then spreads into the Indian and Pacific Oceans, where it may remain isolated from the surface for centuries before gradual mixing and upwelling return it upward. NOAA estimates that a parcel of water can take roughly 1,000 years, and in some descriptions as long as 1,200 years, to complete this planetary scale route. Yet the conveyor belt image should not make you imagine one continuous river following a neat path. The real circulation branches, mixes, slows, changes depth, and exchanges water with neighboring currents, wind, tides, underwater terrain, temperature, and salinity all help shape its motion, while radioactive carbon and other chemical traces allow scientists to estimate how long deep water has remained away from the atmosphere. As the water ages, organisms consume part of its oxygen and release nutrients through respiration and decomposition. So an ancient deep water mass carries a different chemical signature from one that sank recently. This means the circulation does more than move water. It redistributes heat, oxygen, nutrients, and carbon between ocean basins, linking the climate of distant regions through a journey too slow for any human observer to follow from beginning to end. Changes in polar temperature, rainfall, melting ice, and freshwater input can alter the density of surface water and influence parts of this system. Although the global circulation cannot simply switch off like a machine, it consists of interacting pathways rather than one motor and one belt. Its slowness is precisely what makes it powerful. The deep ocean stores the memory of conditions that existed centuries ago, carrying them forward into a climate that may already be different by the time the water rises again. You often imagine the sea responding to the present, the wind blowing now, the storm arriving tonight. But its deepest currents are still completing journeys begun before the modern world existed. The ocean circles the planet not with the urgency of a river, but with the patience of geological time, reminding you that some of Earth's most important movements are too slow to appear as motion at all. The ocean is slowly getting warmer, even at its deepest points. The coldest water on Earth is absorbing heat so quietly that the change may be only a few thousandths of a degree each year. Yet across the enormous volume of the deep ocean, that tiny rise represents an immense transfer of energy. Most human-caused warming first enters through the surface, but currents, sinking water masses, turbulence, and slow mixing carry part of that heat downward. Measuring the result is far more difficult than tracking surface temperature. Satellites cannot directly sense water thousands of meters below. Ordinary profiling floats historically stopped around 2,000 meters, and research ships must repeatedly return to the same remote routes with highly calibrated instruments capable of detecting changes far smaller than the temperature difference between two rooms. These repeat surveys have shown that deep and abyssal warming is real, especially in waters connected to the Southern Ocean and Antarctic bottom water. A refined 2024 analysis found measurable global heat gain in both the deep layer between 2 and 6 kilometers and the abyssal layer below 4 kilometers. While new autonomous deep Argo floats are beginning to provide more continuous observations in places once sampled only years apart, the warming is not uniform. Some basins and depth ranges show stronger increases, while parts of the North Atlantic have experienced cooling or freshening as circulation patterns changed. The title, therefore, does not mean that every trench bottom becomes warmer every year. It means that the global deep ocean is gaining heat overall, with regional exceptions and long periods of variability layered over the trend. Even a small rise matters because warming water expands, adding to sea level rise without requiring any new water to enter the ocean. Temperature changes can also alter density, weaken or redirect currents, affect how much oxygen water can retain, and shift the narrow environmental ranges occupied by animals adapted to remarkable stability. Deep-sea organisms often experience less daily and seasonal temperature variation than life near the surface. So a change that appears numerically tiny to you may be biologically meaningful when it persists for decades. The heat arriving today may also remain stored for centuries, delaying part of the atmosphere's warming while committing the ocean to changes that cannot be quickly reversed. This is the strange bargain of ocean heat absorption. The sea has protected the surface world by taking in most of the excess energy trapped by greenhouse gases, but it has done so by changing its own interior. The deepest water may seem safely separated from smokestacks, roads, and cities, yet climate influence does not need to descend as a visible object. It travels through altered currents and gradually changing water masses, reaching places where no season was expected to change. The abyss is still cold, but cold does not mean untouched, and slowness does not mean safety. The color of the ocean changes with depth in ways human eyes cannot see. The ocean possesses far more colors than the narrow blue world your eyes report, because every meter of water quietly rewrites the spectrum passing through it. Human vision reduces light to signals from only 3 kinds of color-sensitive cone cells, then loses much of that color discrimination as brightness falls and rod cells take over. Scientific instruments do not share this limitation. Spectral radiometers can divide underwater light into hundreds of narrow wavelength bands, revealing changes too subtle for you to name as green, blue, or violet. As light moves through seawater, its optical fingerprint is modified not only by water itself, but by phytoplankton pigments, dissolved organic molecules, mineral particles, bubbles, and microscopic debris. Each absorbs and scatters particular parts of the spectrum differently, so 2 regions that appear almost identical to a diver may contain very different biological communities or concentrations of suspended material. Chlorophyll leaves characteristic absorption patterns, while other pigments used by different plankton groups create smaller signatures hidden inside the broad color your brain interprets. Dissolved organic matter washed from soils can darken water toward tea-like tones, and fine sediments can increase reflection, producing optical changes that instruments detect long before the human eye recognizes a new color. Depth adds another transformation because the remaining spectrum becomes progressively narrower and weaker, while scattering can blur direction and reduce contrast. Underwater cameras, therefore, do not record an objective version of color. Their sensors, artificial lights, distance from the subject, and correction software all influence the final image. An animal photographed as bright red under a submersible lamp may have appeared almost black in the undisturbed environment moments earlier. Modern hyperspectral technology expands this hidden palette even further. NASA's PACE Ocean Color instrument measures more than 200 wavelength bands across ultraviolet, visible, and near-infrared light, including information beyond human sight, allowing researchers to distinguish changes in plankton communities and water properties that would otherwise blend into a single shade. Satellites mainly measure the light that escapes from the upper ocean, while instruments lowered into the water reveal how that signal changes vertically. Together, they turn color into a tool for studying biology, chemistry, and particle movement rather than merely appearance. Yet color itself is not stored inside the water as paint inside a container. It emerges from the meeting between light, matter, and an observer capable of sensing particular wavelengths. A fish with different visual pigments may inhabit an optical world unlike yours, even while occupying the same water. A sensor may detect distinctions neither of you can perceive. So when you look across the sea and call it blue, you are not describing everything the ocean is. You are describing the small portion of its changing spectrum that the human nervous system has translated into experience. Beneath that familiar color lies a hidden map of living cells, dissolved substances, and moving particles, written in shades that surround you without ever becoming visible. Some deep-sea creatures have never been observed alive by scientists. A creature can possess a scientific name, occupy a branch of the animal family tree, and sit inside a museum collection for decades without any human being knowing how it moves while alive. Some deep-sea species are known only from bodies brought up in fishing nets, fragments found inside predators, or preserved specimens collected during old expeditions. Poseidon's squid, Mobidickia poseidoni, offers an extraordinary modern example. Scientists recognized it as a new species, genus, and even an entirely new family in 2025 by re-examining a single specimen collected during the 1950s from the stomach of a sperm whale. No camera recorded the squid swimming, hunting, escaping, or reproducing, so its natural behavior remains almost entirely unwritten. This gap exists because traditional deep-sea sampling often reveals anatomy while destroying context. A net may travel through hundreds of meters of water, collecting an animal without showing the exact depth where it lived, the posture it maintained, or the organisms surrounding it. Fragile bodies can be torn, compressed, or distorted during capture, while changes in pressure and temperature may damage tissues before a specimen reaches the ship. The animal that arrives in a laboratory can therefore resemble evidence left behind after an event, rather than the living being that created it. Scientists may determine what structures it possesses and which relatives it resembles, yet questions about movement, feeding, courtship, color, and defensive behavior remain unanswered. Remotely operated vehicles have begun closing this divide. One deep-sea anglerfish described from a specimen collected in 1891 was not observed alive in its natural environment for more than a century. When researchers finally filmed it, they discovered that it could move across the bottom in a walking motion and lived much deeper than trawl records had suggested. Such encounters demonstrate why a preserved body is never a complete biological story. Even color can change after death. Transparent tissues can become cloudy, Delicate appendages may disappear, and organs shaped by pressure can collapse near the surface. A species may therefore be classified correctly, while its actual appearance remains partly misunderstood. The difficulty is not simply reaching great depth, but being in exactly the right place during the brief moment when a rare animal passes through a camera's narrow field of view. Research vehicles can spend thousands of hours underwater and still encounter certain species only once. Others may migrate vertically, hide within sediment, occur in isolated basins, or exist at densities so low that decades pass between collections. When scientists say an animal has never been observed alive, they do not mean that it has lived without being seen by any eye. Predators and members of its own species have interacted with it throughout its history. They mean that human knowledge has reached the body but not the life. Somewhere below, a named creature may be performing behaviors no textbook contains, carrying out an ordinary existence that remains extraordinary only because no human witness has arrived. The ocean floor is covered in the remains of ancient creatures. What appears to be pale mud across parts of the ocean floor can be made largely from the skeletons of organisms too small to see without magnification. Vast regions are coated in biogenic ooze, sediment formed when the hard shells and supporting structures of microscopic life settle and accumulate over long spans of time. Foraminifera and coccolithophores build structures from calcium carbonate, while diatoms and radiolarians produce intricate frameworks from silica, the same basic material associated with glass. After these organisms die, their soft tissues are usually consumed or decomposed, but many of their mineral remains continue downward and eventually become part of the seabed. In a long-running sediment trap study in the Sargasso Sea, roughly 70% of the material collected at a depth of about 3,200 meters consisted of carbonate or siliceous shells and skeletal fragments from minute organisms. Under a microscope, this supposed mud becomes a field of spirals, chambers, plates, needles, and lattices, each structure once produced by a living cell. Yet the remains are not distributed evenly across every ocean basin. Calcium carbonate shells dissolve more readily as they descend into colder, deeper, and more chemically corrosive water. Below a depth known as the carbonate compensation depth, calcium carbonate can dissolve faster than it accumulates, so the deepest seabed may contain little calcareous ooze, even when countless shells were produced above it. Silica behaves differently, allowing the remains of diatoms and radiolarians to dominate in regions where those organisms are highly productive or where other sediments arrive slowly. Near continents, mineral grains delivered by rivers, winds, glaciers, and underwater landslides may bury or dilute biological remains. Far from land, where rock-derived sediment is scarce, the skeletons of microscopic organisms can become one of the main materials constructing the floor. As burial continues, pressure and chemical change can eventually transform loose ooze into solid rock, such as chalk, limestone, or chert. Some cliffs now standing on land began as ancient marine sediments assembled from lives that once drifted in vanished seas. This means a landscape can be built from organisms that never knew they were building anything. Each contributed a structure smaller than dust, yet accumulated generations produced layers thick enough to enter the geological record. Their preserved forms also allow researchers to identify past ocean conditions because different species favored different temperatures, nutrient levels, and water masses. A change in the shells found within a core may reveal that currents shifted, surface waters cooled, or a biological community reorganized thousands or millions of years ago. But even without reading that history, the material itself changes how you imagine the ground beneath the sea. It is not always an inert platform upon which life happens. In many places, it is partly made from life, assembled cell by cell until countless vanished organisms become the surface supporting those that exist today. Whale falls create entire ecosystems that last for decades. When the body of a whale reaches the deep sea floor, death arrives carrying enough stored energy to transform an ordinary patch of sediment into a changing community that may endure for decades. The process begins before the carcass is visible to most animals. Oils and dissolved compounds spread through the water, and mobile scavengers follow the chemical trail from far away. Hagfish, sharks, large crustaceans, and other feeders can gather around the body, removing skin, muscle, and organs over months or sometimes years, depending on the whale's size, depth, temperature, and the number of visitors. This first stage is dramatic but temporary. Once most of the flesh is gone, smaller organisms occupy the nutrient-rich sediment surrounding the skeleton. Worms, mollusks, and crustaceans consume fragments left behind and take advantage of organic material that has soaked into the seabed. The carcass is no longer simply food lying upon the ground. It has chemically changed the ground beneath it. A later stage begins when bacteria gain access to the large quantities of fat stored within the bones. As that material is broken down under low oxygen conditions, hydrogen sulfide is produced, creating an energy source for sulfur-using microbes. These microorganisms support a new community that can include mussels, clams, snails, and specialized worms, allowing the skeleton to function almost like a temporary chemical oasis. This final phase can continue for several decades because the enormous bones release their stored lipids slowly. The sequence is not identical at every whale fall. A smaller carcass may be consumed rapidly, an exposed skeleton may be scattered by currents, and local species differ between basins and depths. Some scientists also recognize a later reef stage, when most usable organic material has disappeared, but the remaining bones provide hard surfaces and shelter in an environment dominated by soft sediment. The whale has then stopped functioning mainly as food, and begun functioning as architecture. One carcass can attract hundreds of species across its succession, with different groups arriving as each previous resource is exhausted. Researchers have intentionally placed whale remains on the seabed and returned over many years to watch these transitions, discovering that a single death can create a long experiment in ecological change. Whale falls may also act as stepping stones between widely separated habitats, giving certain organisms temporary islands from which their descendants can disperse. Their importance is measured not only by how much flesh they provide, but by how long they continue altering relationships around them. A whale may spend decades moving through the upper ocean, then support another sequence of lives for a comparable period after sinking. Its body changes from animal to feast, from feast to chemical engine, and from chemical engine to structure. What appears to be an ending from the surface becomes, on the seafloor, a succession of beginnings, each community arriving because the one before it has transformed what remains. A single dead whale feeds hundreds of species on its way to the bottom. The death of a whale can transfer decades of stored energy from the upper ocean into a single concentrated point thousands of meters below. But the phrase, "on its way to the bottom," hides an important truth. Most of the feeding begins after the body has landed. A large whale may weigh tens of tons, carrying within its muscles, organs, skin, and oil-rich bones an amount of organic material that would normally reach the deep sea floor only as scattered particles over many years. If the carcass remains intact and sinks rather than washing ashore, it delivers this energy in one sudden package. During the descent, sharks, fish, seabirds, and microorganisms may remove or decompose some tissue, but a whale can sink rapidly enough for much of its body to arrive below. Once there, its chemical scent spreads through the water and sediment, attracting mobile scavengers from the surrounding darkness. The title's claim of hundreds of species is plausible across the full life of a whale fall, although not every individual carcass will host the same number. More than 400 species have been recorded in association with whale fall environments, and a single large skeleton may support an unusually rich mixture of visitors. Residents, parasites, predators, microbes, and animals found almost nowhere else. The whale does not feed them all in the same way. Some consume flesh directly, others eat organisms attracted to the carcass, and many benefit indirectly from nutrients entering the nearby sediment and food web. Carbon once gathered through years of feeding is divided among bodies of dramatically different sizes. from large scavenging fish to bacteria invisible without a microscope. Some of that carbon is breathed back into the water, some becomes new animal tissue, and some is buried in sediment or retained in bones, linking the whale to long-term ocean carbon storage. Its body also creates opportunity through rarity. In much of the deep sea, food arrives in small, unpredictable amounts. So a carcass of this size is not simply a meal, but a temporary concentration of biological possibility. Animals that might otherwise remain separated across a broad plain can gather around the same source, producing interactions that would rarely occur elsewhere. Yet calling the whale generous would place human intention upon a natural process. It did not choose to provide a feast, and the organisms do not mourn the life that produced it. They recognize usable matter and convert an ending into movement, growth, competition, and reproduction. The whale that once traveled across an ocean continues influencing it after motion has stopped, not as one animal, but as energy redistributed through hundreds of other lives. Death does not preserve the body's boundaries. It opens them, allowing what was once contained within a single creature to become part of an entire community. The bones of ancient sea creatures are preserved in deep ocean sediment. A bone buried beneath the sea does not automatically become a fossil. It must survive a long sequence of events designed, in effect, to erase it. After a marine vertebrate dies, scavengers can separate the skeleton. Currents may scatter its elements, microorganisms enter its pores, and specialized animals can consume the fats and proteins stored inside. Seawater also interacts chemically with the mineral structure, while slow sedimentation may leave the remains exposed for years before burial. This is why the fossil record of ancient whales, fish, sharks, dolphins, and marine reptiles is not a complete cemetery of everything that ever lived. Most bodies disappear without leaving a durable trace. Exceptional preservation begins when local conditions interrupt that destruction. Rapid burial beneath mud or sand can protect bones from large scavengers and physical movement. If oxygen becomes limited inside the surrounding sediment, decomposition may slow, and the chemical environment can encourage new minerals to form within or around the skeleton. Calcium phosphate may reinforce bone, while carbonate minerals can grow into a concretion that seals the remains inside a hardened mass. Such a structure acts like a natural case, supporting fragile cavities, limiting compaction, and separating the fossil from later water movement. Scientists study these processes through taphonomy, the science of what happens to an organism between death, burial, discovery, and interpretation. Even bones belonging to the same animal can preserve differently if one section is buried quickly while another remains exposed. A complete-looking skeleton may have lost much of its microscopic structure, while an isolated fragment can retain remarkable chemical or cellular detail. Deep ocean fossils also face a limitation created by plate tectonics. Nearly all very old oceanic crust and its sediment have eventually been carried into the earth. So the present open seafloor generally does not preserve an uninterrupted record extending back through the entire age of animal life. No surviving oceanic lithosphere is much older than about 180 million years. Many spectacular fossils of ancient marine creatures are therefore discovered in sediments that formed beneath former seas, but were later uplifted onto land, as happened in fossil-rich marine formations in Peru and elsewhere. Their presence on a desert hillside does not make them terrestrial animals. It reveals that the seabed itself moved into daylight. When researchers do recover bones from modern deep-sea sediment, the remains may be recent, partly mineralized, or in the early stages of entering the fossil record. Fossilization is not a moment when bone suddenly turns to stone. It is a prolonged negotiation between decay and protection, during which original material may survive, be replaced, or become enclosed by new minerals. What reaches a museum is therefore not simply an ancient skeleton that waited unchanged. It is the rare survivor of chemistry, scavenging, burial, pressure, erosion, and geological movement. Every preserved bone represents not only the creature that once carried it, but also a sequence of unlikely conditions that allowed part of that creature to escape the ordinary fate of disappearance. The deep ocean has barely changed in millions of years. The deep ocean feels timeless because its days do not bring sunlight, weather, or dramatic seasonal change, yet over millions of years it has been repeatedly transformed. Compared with a beach or a forest, many deep environments are extraordinarily stable over short human timescales. Temperatures fluctuate little, storms may have no direct effect, and some sediments accumulate with almost unimaginable slowness. These conditions help explain why certain body plans and ecological strategies can remain recognizable for very long periods. But stability is not the same as immobility, and the claim that the deep ocean has barely changed becomes misleading when viewed across geological time. Evidence preserved in microscopic fossils and sediment chemistry shows that deep water was once much warmer than it is today. During the early Eocene, around 50 million years ago, average deep ocean temperatures may have approached 12 degrees Celsius in some reconstructions. Compared with the near-freezing conditions common across much of the modern abyss, long-term cooling accompanied the growth of major ice sheets, while shorter climatic cycles caused deep water temperatures to rise and fall by several degrees. Oxygen levels also changed as circulation weakened, strengthened, or shifted between regions. Some ancient oceans developed widespread oxygen pore zones that reorganized ecosystems and altered the burial of carbon and nutrients. The opening and closing of ocean gateways changed where water could flow. Continents moved, basins widened or vanished, and currents that now seem permanent did not yet exist in their present forms. Sediment records from the Miocene reveal major reorganizations in deep circulation and in where different kinds of biological material accumulated. Even over the last 130,000 years, fossil communities on the seafloor changed with temperature, showing that deep-sea biodiversity responds to climate rather than remaining frozen outside history. The seabed itself has also been renewed and destroyed, meaning most of the ground beneath today's ocean did not exist when many famous ancient animals were alive. What appears unchanged is often only changing too slowly for a human lifetime to register. A coral colony may experience stable water for centuries while the basin carrying it gradually shifts. A species may preserve an ancient-looking form while its genes, physiology, distribution, and relationships continue evolving. The deep sea is therefore not a museum sealed against time. It is more like a long exposure photograph in which rapid surface events blur away, while slower transformations remain visible. Its calmness is real but relative. Over a day, almost nothing may seem to happen. Over 50 million years, water cools, circulation reorganizes, oxygen rises and falls, communities migrate, and entire sections of seafloor disappear into the planet. The illusion of permanence comes from comparing geological motion with a life too brief to witness it. The deep ocean has changed repeatedly. It has simply done so without needing anyone to watch. Some ocean trenches are so deep that light from the surface is only a memory. At the bottom of a Hadal trench, sunlight is not merely faint or hidden behind darkness. No photon arriving from the surface has survived the journey to reach you. These trenches descend between 6 and 11 kilometers beneath the sea, far below the depth at which water has absorbed and scattered the final traces of solar light. The phrase "only a memory" is poetic, because most animals born there have never personally experienced daylight and may possess no concept of a bright surface world. Yet sunlight can still reach them in another form. Organic matter created in illuminated waters sometimes sinks into trenches inside dead organisms. Waste particles, wood, or sediment swept downward by landslides. The original photons are gone, but some of the energy they helped living cells capture remains stored in chemical bonds. A scavenging amphipod feeding on that material is therefore using a distant inheritance from sunlight without ever seeing light itself. Trench topography can intensify this process. Steep walls guide loose sediment toward the lowest depressions, while earthquakes can trigger sudden flows that carry material from shallower regions into the Hadal environment. Food may arrive not as a gentle, even supply, but as rare pulses separated by long periods of scarcity. This creates a world organized by events that begin far outside it. A storm may increase material sinking from upper water. A landslide may bury one community while feeding another. The body of an animal may deliver nutrients to a place where local production is limited. Any visible glow in this realm must come from a nearby organism, a chemical process, or the lamps of a visiting machine, rather than from the sun. Some deep-sea fishes possess unusually complex sets of light-sensitive proteins that may help them interpret the narrow colors produced by living sources, showing that the disappearance of sunlight does not necessarily make vision useless. It changes what vision is for. An eye no longer studies landscapes shaped by daylight. It waits for a brief biological signal that may reveal food, danger, or another member of the species. Even time loses one of its most familiar markers. Sunrise and sunset cannot divide the day, although tides, currents, feeding events, and inherited biological rhythms may still produce cycles of activity. The trench is therefore not disconnected from the surface, but connected through delayed consequences rather than direct illumination. Energy, matter, and physical disturbances descend into it long after the light itself has vanished. You might imagine the bottom as a place where the sun has been forgotten, but the truth is more subtle. The sun can influence a world that has never seen it, surviving not as brightness, but as chemistry carried downward through the bodies and debris of other lives. The last unknown creatures on Earth are almost certainly in the deep ocean. The final undiscovered animals on Earth are unlikely to be giant monsters waiting in open water. They are far more likely to be tiny, soft, buried, parasitic, or so similar to known species that only their genes reveal the difference. The deep ocean is one of the strongest candidates for this hidden biodiversity because it combines enormous volume with isolated trenches, submerged mountains, deep sediments, and habitats that may have been sampled only once or never. Ocean Census estimates that as many as 2.2 million marine species may exist, while fewer than 10% have been formally documented, although such totals remain estimates rather than completed counts. Recent work shows how quickly the known inventory can grow when scientists examine neglected regions carefully. By May 2026, the Ocean Census Network reported 1,121 previously unknown marine species, including corals, worms, crustaceans, anemones, echinoderms, and deep water fishes collected from environments extending more than 6 kilometers down. Yet finding a creature and establishing a species are separate achievements. A specimen must be examined, compared with existing descriptions and museum collections, often genetically analyzed, formally named and published, so other researchers can test the conclusion. The process currently takes an average of around 13 years, meaning some unknown species may already be sitting in jars, freezers, photographs, or DNA databases while awaiting the expertise needed to recognize them. Environmental DNA is making the mystery even larger. Animals constantly release cells, mucus, waste, eggs, and fragments of tissue into water and sediment. Researchers can collect this material and detect genetic sequences belonging to organisms they never directly see. But an unfamiliar sequence does not automatically reveal the body that produced it. It may point to a new species without telling scientists its appearance, behavior, abundance, or ecological role. Sediment-dwelling organisms are especially easy to miss because many live between individual grains, while parasites and symbiotic animals can spend most of their lives hidden inside other creatures. Large unknown predators are less probable because large bodies require food, breeding populations, and ecological effects that tend to leave tracks, remains, genetic traces, or repeated sightings. The greatest undiscovered diversity may therefore be composed of lives that are not dramatic to the eye, but are essential to nutrient cycling, decomposition, disease, and food webs. The title also deserves caution. Unknown species continue to be discovered in caves, soils, forests, fresh water, and even familiar coastlines. So the deep ocean does not possess a monopoly on mystery. It simply offers more unexplored habitat than almost any other realm. The last creatures added to humanity's catalogue may have existed beside one another for millions of years without needing a name. Their unknown status describes a limit in human observation, not an incompleteness in nature. The ocean is already full of them. It is our picture of life that still contains the empty spaces. The ocean floor is the quietest place on Earth, and also the loudest. Set a microphone on the deepest sea floor during calm conditions, and it may record an acoustic stillness difficult to find near any city. Yet leave it there long enough, and the same instrument can hear earthquakes, storms, whales, ships, and distant geological violence arriving from thousands of kilometers away. This is why the ocean floor can be described as both extraordinarily quiet and surprisingly loud, although neither description is universally true. Quietness depends on location, weather, biological activity, shipping, instrument sensitivity, and the range of frequencies being measured. At Challenger Deep, researchers deployed a pressure-resistant hydrophone more than 10 kilometers below the surface, expecting strong acoustic isolation. During calm periods, the trench could indeed become relatively quiet, but 3 weeks of recordings revealed that it was not sealed from the rest of the planet. The instrument detected nearby and distant earthquakes, whale vocalizations, passing ships, and the influence of severe weather moving across the surface far above. Low-frequency sound travels efficiently through water, so a silent patch of mud may receive vibrations from an event occurring beyond every visible horizon. The deepest point can therefore be locally motionless, while remaining acoustically connected to entire ocean basins. Sudden events also create extremes. A submarine earthquake can move enormous sections of crust. A volcanic eruption can fracture rock and release gas. An iceberg can crack with enough energy to be detected across an ocean. And the implosion of an unprotected pressure vessel can produce a sharp pulse that travels far from the point of collapse. These sounds may be intense at their source, even though they become faint by the time a distant sensor records them. Comparing underwater loudness directly with sound in air is also misleading, because acoustic measurements in water use a different reference pressure. An underwater value expressed in decibels cannot simply be compared number for number with the decibel reading of a concert or aircraft. The environment's reference units and way sound enters an ear are different. The paradox is therefore not that the seafloor is constantly louder than everything on land. It is that an environment capable of extraordinary calm can also function as a listening chamber for planetary scale events. Between those events, a hydrophone may hear only a low background made from distant water movement, faint biological activity, and the instrument's own limits. Then the crust shifts, a storm crosses the ocean, or a ship passes thousands of meters above, and the apparent silence reveals that it was never isolation. The deepest seafloor does not generate every sound it receives. It gathers them, allowing a single location to become quiet in itself, while carrying evidence of a restless world far beyond it. Silence there is not the absence of events. It is the space between messages traveling through the planet. Life in the deep ocean has found ways to survive that defy every expectation. A living cell at the bottom of an ocean trench survives only because nearly every part of its internal machinery has been rebuilt for a world that would distort ordinary biology. Immense pressure does not simply push on the outside of an animal. It changes how water surrounds molecules, interferes with the folding of proteins, and can force delicate cell membranes into shapes that prevent them from functioning normally. Deep-sea organisms answer this threat through layers of adaptation that remain invisible from the outside. Many fish accumulate protective compounds such as trimethylamine N-oxide or TMAO, which helps proteins maintain useful structures under pressure by altering the behavior of the water around them. Concentrations of this compound generally increase as fish live deeper, suggesting that survival requires progressively stronger molecular protection. Cell membranes must also be carefully constructed. If their fats become too rigid, essential proteins cannot move and transport materials properly. If they become too loose, the membrane loses control of what enters and leaves. Recent studies of pressure-adapted animals show that survival depends not merely on making membranes more fluid, but on using particular lipids that preserve their curvature and organization under compression. Deep-sea microbes reveal an even more radical possibility. Some are piezophiles, organisms that grow best under high pressure, while obligate piezophiles may perform poorly or fail to grow when brought into ordinary surface conditions. To them, the environment that protects your body is itself abnormal. Their enzymes, repair systems, metabolism, and cellular structures are tuned to forces that laboratory glassware must recreate before scientists can study them properly. Hadal snailfish add another set of solutions. Their bodies are soft, their skeletons are lightly mineralized, and genomic studies have identified changes associated with protein stability, membrane function, sensory biology, and the management of cellular stress. Yet adaptation does not remove all limits. Fish disappear before the deepest trench floors are reached, and one explanation is that maintaining enough protective TMAO eventually creates its own chemical and osmotic difficulties. Microbes and invertebrates can continue deeper because they solve pressure in different ways, reminding you that there is no single invention called deep-sea survival. Every lineage negotiates separately with the same physical problem. The title says these creatures defy every expectation, but they do not violate nature's laws. They expose how narrow human expectations were. You instinctively define a comfortable environment by the conditions that keep your own proteins folded, your membranes stable, and your organs functioning. Deep life shows that those conditions are not universal standards. They are only one biological arrangement among many. What seems impossible from the surface becomes ordinary once evolution has had enough generations to reshape chemistry itself, until the crushing world below is no longer an extreme place to endure, but the only place where a body truly belongs. The deep ocean may hold clues to how life first began on Earth. Before the first cell could inherit genes, divide, or evolve, lifeless matter somehow had to begin organizing energy into chemistry that could sustain itself. And the deep sea floor may preserve one of the most compelling settings in which that transition could have occurred. The strongest version of this idea focuses not on the extremely hot black smoke as commonly imagined, but on alkaline hydrothermal systems created when seawater reacts with certain mantle rocks in a process called serpentinization. These reactions can produce hydrogen, heat, and highly alkaline fluids that rise through mineral structures and meet a more acidic ancient ocean. Where the two fluids encounter one another, natural differences in chemistry arise across thin mineral walls. Modern cells use comparable differences across their membranes to power essential reactions, leading some researchers to propose that early life inherited an energy system that geological vents had already created before biology existed. The porous mineral structures of alkaline vents may also have provided tiny interconnected chambers where molecules could become concentrated instead of being immediately diluted into the open ocean. Iron and sulfur-bearing minerals within those walls can act as catalysts, helping reactions occur that would otherwise proceed too slowly. Laboratory experiments have shown that metals and vent-like conditions can promote parts of simple carbon-fixing chemistry, while artificial vent systems demonstrate how natural pH differences can drive reactions and electrical currents across mineral barriers. None of this proves that life began there. A successful origin must explain far more than the creation of a few organic molecules. It must account for information storage, self-copying chemistry, enclosed membranes, metabolism, error, inheritance, and eventually natural selection. Critics of the vent hypothesis also note that some important prebiotic reactions may benefit from ultraviolet light, repeated drying and wetting, freezing, or concentrated surface environments that a permanently submerged vent cannot easily provide. The first living system may therefore have emerged in another setting, or through materials and reactions moving between several environments rather than remaining in one birthplace. What the deep ocean offers is not a preserved fossil of the first organism, because soft primitive chemistry would have left almost no recognizable remains. It offers a functioning geological analogy: water meeting rock, minerals creating compartments, hydrogen supplying chemical energy, and natural gradients performing work without sunlight or life. These features allow scientists to test whether the planet itself could have acted as a primitive reactor before cells learned to carry such reactions within their own boundaries. The deepest question is therefore not whether a vent once produced a finished organism. It is whether geology slowly taught matter the habits that biology later made its own. Perhaps life did not begin when dead materials suddenly became alive, but when a restless Earth created chemical systems that persisted, repeated, and grew increasingly capable of preserving their own continuation. The deep ocean may not contain the final answer, yet it shows how the boundary between rock and life could have been crossed through many small reactions rather than one impossible leap. Scientists believe the deep ocean may be the best place to search for life on other worlds. The most promising alien habitat in our solar system may not lie beneath a colored sky or across a dusty surface, but inside an ocean sealed under kilometers of ice where no telescope can look directly. Scientists are especially interested in Jupiter's moon Europa and Saturn's moon Enceladus, because both are believed to contain global bodies of liquid water beneath frozen crusts. Europa's ocean may hold roughly twice as much water as all of Earth's oceans combined, while the flexing caused by Jupiter's gravity can provide heat that helps prevent the interior from freezing completely. Enceladus offers an even more unusual advantage. Fractures near its south pole release jets of water vapor and ice grains into space, allowing a spacecraft to sample material connected to the hidden ocean without drilling through the surface. NASA's Cassini mission detected salts, simple and complex organic compounds, molecular hydrogen, and evidence of active interaction between water and warm rock. Researchers have also identified phosphates within plume-forming ice grains, suggesting that phosphorus, an element required by all known Earth life, may be readily available in the Moon's ocean. These discoveries are not evidence that organisms exist there. Water, organics, hydrogen, and phosphorus can all occur without biology. Together, however, they indicate that Enceladus possesses several ingredients scientists consider important for habitability: a long-lived liquid environment, useful chemistry, energy sources, and likely contact between ocean water and a rocky interior. Europa may offer a related but differently structured laboratory. Its surface ice is exposed to intense radiation from Jupiter, which can create chemically reactive compounds. If some of those materials are transported downward, while products from the ocean move upward through cracks or slowly overturning ice, the Moon could maintain chemical imbalances capable of supporting metabolism. NASA's Europa Clipper mission is designed to investigate the thickness and structure of the ice, the composition of the surface, the properties of the ocean, and possible locations where conditions might support life. It is explicitly a habitability mission rather than a direct life detection mission, an important distinction in a field where promising chemistry can easily be mistaken for a biological discovery. Earth's deep ocean provides the closest accessible guide for interpreting these worlds because it demonstrates that ecosystems can exist without direct sunlight, that water-rock reactions can supply usable chemical energy, and that life can remain active beneath conditions once considered too dark, cold, or pressurized. But Earth is only an analogy, not proof. Europa and Enceladus have different gravity, rock composition, ocean chemistry, histories, and available energy. Their oceans may be habitable but empty, or life may have begun there through processes unlike anything preserved on Earth. The ocean has been on Earth longer than the continents. Before Africa, Asia, or any coastline you would recognize existed, liquid water may already have been moving across the surface of the young Earth. The title is broadly true when continents means the large, stable landmasses of the modern world, but the earliest history is more complicated than an ocean appearing first and dry continents arriving much later. Earth formed about 4.5 billion years ago as a hot world repeatedly struck by other objects, its surface initially hostile to lasting oceans. Water may have arrived partly within the materials that built the planet and partly through later impacts, while volcanic gases released additional water vapor from the interior. As the surface cooled, vapor condensed, rain fell, and water collected in low regions. Tiny zircon crystals preserve chemical evidence suggesting that liquid water was interacting with Earth's crust around 4,300 million years ago, only a few hundred million years after the planet formed. Some zircons are even older and indicate that silica-rich continent-like crust may also have existed remarkably early. This means the first oceans and the earliest fragments of continental crust probably developed together, influencing one another from near the beginning rather than appearing as two perfectly separated stages. Those first patches of land were not versions of the continents you know today. They may have been small volcanic plateaus, island-like blocks, or unstable pieces of crust repeatedly melted, buried, broken apart, and joined into larger structures. Over billions of years, continental fragments collided to form supercontinents and later separated again. The positions of coastlines changed so completely that places now far inland were once underwater, while former seafloors were lifted into mountain ranges. Even the ocean basins themselves were temporary. The present Atlantic did not exist when the earliest dinosaurs appeared, and nearly all of today's seafloor is younger than the ancient cores preserved inside continents. Water is older than those modern basins because the ocean survives even as the containers holding it are continually replaced. It moves between basins, enters minerals, freezes into ice, rises into the atmosphere, returns as rain, and sometimes travels into Earth's interior before emerging again. The oldest ocean was probably different in temperature, chemistry, depth, and appearance, and no sample of its original seafloor remains intact for scientists to examine directly. Its existence must be reconstructed from minerals that survived after the rocks around them were destroyed. That makes the ocean's age strangely difficult to see. Continents display ancient stones at the surface, while the older history of water is preserved only through subtle chemical signatures inside crystals. You stand upon land that seems permanent and look toward water that appears restless. Yet geological time reverses those impressions. The continents are temporary arrangements of older fragments, while the ocean is a continuing planetary presence whose shores have moved through countless shapes. The water beside a modern beach is not physically the same collection of molecules that fell on the early Earth, but it belongs to a cycle that began before any familiar continent had a name, an outline, or perhaps even a stable place above the waves. Everything on the surface of the Earth has been shaped by the ocean beneath. The mountains above you may contain water that once disappeared into the sea floor, descended beneath a continent, and helped generate molten rock far below the surface. It would be inaccurate to say that literally everything on Earth has been shaped only by an ocean lying underneath it, because wind, ice, impacts, biology, and the planet's internal heat all transform the surface. Yet the ocean participates in far more of the landscape than its visible shorelines suggest. Seawater enters cracks in oceanic crust, reacts with hot rock, and becomes stored within newly formed minerals. Sediments soaked with water also accumulate upon the moving plate. When this oceanic plate eventually descends beneath another plate, it carries part of that water into the Earth, not mainly as underground lakes, but chemically bound inside minerals. Rising temperature and pressure destabilize those minerals, releasing fluids into the overlying mantle. This added water changes the melting behavior of hot rock, allowing magma to form more readily than it otherwise would. Some of that magma rises and feeds volcanic arcs, such as those surrounding much of the Pacific. Repeated eruptions add new material to the crust, while collisions compress, thicken, fracture, and lift the land into mountain chains. The connection means that water once absorbed by a dark seabed can later help construct volcanoes that rise into clouds. The same system produces some of the planet's most powerful earthquakes, because descending plates can remain locked against the plate above until accumulated stress is released. Even far from these boundaries, the ocean continues shaping the visible world. Evaporation supplies much of the moisture that later falls over land as rain or snow. Rivers use that water to cut valleys, move minerals, build floodplains, and carry the broken remains of continents back toward the sea. Waves reshape coastlines, but sea level also determines where rivers end, where sediments collect, and which portions of continental shelves are exposed or drowned. During periods of lower sea level, rivers extended across land now submerged. When water rose again, those valleys became bays, estuaries, and underwater channels. Ocean circulation redistributes heat, altering rainfall patterns and helping determine where deserts, forests, and ice can persist. The sea therefore shapes the land both mechanically and indirectly through erosion, climate, chemistry, and the hidden transfer of water into the deep earth. Scientists are still working to determine how much water descends past volcanic regions and how much reaches deeper parts of the mantle, because some is released early, while some may remain trapped in minerals capable of surviving greater pressures. This deep water cycle is measured over millions of years rather than seasons, connecting rainfall and seawater to processes occurring far below any human well. The ocean you see is only the exposed portion of that relationship. Some of its water is inside clouds, living cells, rock pores, ice, magma-producing regions, and minerals descending toward the mantle. The surface of Earth was not sculpted by water acting alone, but it has been shaped by a planet in which water refuses to remain at the surface. It enters stone, changes its behavior, helps break continents apart, assists in building new crust, and eventually returns through springs, erosion, and volcanic gases. The ocean is not merely beside the land. Through a cycle hidden beneath both, it has become one of the materials from which the land's continuing story is made. The deep ocean is still mostly unknown, and that may never change. The final mystery of the deep ocean is not simply that we have failed to visit most of it, but that the world we are trying to understand changes while we are still learning how to observe it. New mapping systems, autonomous vehicles, environmental DNA, long-term sensors, and remotely operated machines will continue reducing enormous gaps in knowledge. So it would be wrong to claim that the ocean must remain as unknown as it is today. A global strategy published in 2026 proposed thousands of carefully distributed exploration sites intended to correct the severe geographical imbalance of previous observations. That imbalance matters because much of the available visual record comes from regions near a relatively small number of wealthy nations and research institutions. If scientists repeatedly visit similar areas, the resulting picture of a typical deep ocean may reflect convenience rather than reality. Even a perfectly balanced survey would not complete the task. A map reveals shape, but not necessarily the organisms living there, the chemistry moving through sediment, or the events occurring between visits. A camera records only the animals present within its lights at that particular moment. A species may migrate through the area a day later, reproduce only once a year, emerge from sediment during a rare disturbance, or pass through the frame too quickly to be recognized. Microbes and tiny animals can inhabit spaces between grains of mud, while life may extend beneath the seafloor into buried sediments and fractured rock that no ordinary camera can examine. Geological events can also transform a location after it has been studied. Earthquakes trigger landslides, currents relocate sediment, eruptions create fresh surfaces, carcasses appear and disappear, and changing water masses alter temperature, oxygen, and food supply. Returning to the same coordinates may therefore mean encountering a different environment. Technology creates its own limitations. Tethers restrict where some vehicles can travel. Batteries limit autonomous missions. Instruments can fail under pressure, and transmitting large amounts of data through water remains difficult. Samples brought upward may change before reaching a laboratory, while artificial lights, noise, and movement can alter the behavior researchers hope to observe. Every method reveals certain features while hiding or disturbing others. This does not make exploration futile. It makes knowledge dependent on repeated observation from many perspectives. Scientists can eventually build excellent maps, classify vast numbers of organisms, monitor representative habitats, and explain many of the processes operating in the deep.